Hey guys, wish you all a very good evening and welcome to this second class on Transformers. Cool. So I got the OTP 6374. Awesome. So I believe I'm audible and my screen is readable. So great. We're all set for our class. Cool. As usual, let's wait for a couple of minutes before we get started. It's kind of important for people to join in today. Yeah, we're going to learn about some very powerful neural network architectures. So yeah, and it's kind of important for us to understand the terminology over here because I'm pretty sure there are quite a lot of blogs and good tutorials which teach you these things. But once we're familiar with the terminology, I believe it gets easier to understand what they're talking about. So the focus of today is going to be looking at each terminology, how it's implemented, and how we finally get our outputs from the network. So yeah, that's going to be the focus for today. In the meantime, I hope you guys had a chance to revise the concept of attention. It would be a bit difficult for me to go through that again. I will try my best. Like we could revisit the visualizations if needed, but yeah, cool. Awesome. Hey, hi, good evening, Azhar. So just a minute more and we'll get started, guys. Hmm. In the meantime, any feedback, any comments that you guys want to discuss? How are you feeling at the start of a week, new week? Hope everyone is doing well. Not so well. Why? What happened, Ajay? Monday blues? Yeah, I can understand that. Like weekends go so well, right? Deployment, I see. Yeah, a lot of workload. I can imagine. Okay. But what's good is like, the Transformers concepts can be understood at like a high level concept, and then we'll dig deep, right? So Ajay, if you can follow along at least for the high level concepts, right? Maybe when you get actual time, you can look at the details of the implementation. So maybe try doing it that way. If you are tired by your deployment or you're distracted, my request is just follow the major component discussions. So we'll see what a transformer architecture looks like. It's very mysterious. Like you will see these self-head, multi-head attention, self-attention, cross-attention. Hundreds of terminologies are there, but if you understand at a high level what is being done, right, it gets much easier to appreciate why it's being done. So my only request is if you are getting distracted, if you're not able to focus on the detailed explanations, right, at least try and pay attention to the overall thing. So that's my request. Okay, cool. So we're 5 minutes into our lecture. Let's get started, guys. Awesome. So let's begin with our usual recap. What we majorly studied last class was how do you take an RNN model and how do you apply attention on it, right? Attention at the fundamental level fixes two problems with the RNN architecture, right? Last class, we took examples from an RNN that we had trained ourselves, right? And we had seen that there are two specific problems with this. Can you guys quickly remind me what the problems are? Anyone who wants to remind me what the problems with the typical, yeah, the recall part, right? So the first problem is a lot of information gets overwritten in an RNN. Okay. So the major issue there is that we have a single state, a hidden state, and which has to encode the whole information in your input sequence, right? So it is very likely that sometimes your RNN can forget important details. So if you remember the Facebook example, what it was supposed to tell us was Canadian firm. What it actually told us was Facebook again. So it was trying to recollect the name of a company. It recollected the name of the company it saw more times rather than the company which was relevant over there, right? So this is known as the recall problem. Okay. What is the other problem? In case you guys remember. Any other problem? Something to do with the alignment? Something to do with are the correct words being recalled at the same time, at the correct time, right? That was another example that we had seen in the last class. We saw that an RNN is not able to align or correctly pick out the right information at the right time, right? The recall is one part of it, but then the alignment, like uh, it turns out that to summarize a document, you may have to pay attention to the first three sentences and not so much attention to the last three. Yeah, not so much attention on the last three, right? So this is what I mean by the alignment problem. What an RNN tries to do is it tries to use information from the whole text. It is very unbiased, right? In the sense that it will try and recollect whatever it has seen from the entire text, whereas for summarization, some parts are best ignored, right? So that is known as the alignment problem. The correct the focus is not going to the right place while summarizing, right? We saw these two problems, and then we said that okay, these are the two problems with an RNN. What will we do now? We can now improve the way RNNs are able to recall and improve the focus that the RNN is giving on the correct parts of your input text. We can do this using a mechanism known as attention, right? And last class specifically, we discussed how we are going to do that. So in a typical encoder decoder architecture, you have hidden states of your encoder, you have hidden states of your decoder, right? So to give you a brief recap on how we apply attention on RNN, okay, the type of attention that we apply is single head attention. What do I mean by single head? There is going to be a single key matrix, a single query matrix, and a single value matrix. So if we have just single matrices of these types, if we put them together and do all the 6 steps that are required to generate context vectors, we will get our attention outputs, right? Okay. That is apply essentially applying single head attention on output. Bad attention. All right. Am I audible now? Guys, is this better? Please hit a yes if this is better. I refreshed my screen. There didn't seem to be an internet problem. I think it was a problem with my Bluetooth headset. Let's do one thing. Just for the safe side, I'm going to disable my video for now. If this is better, then we can go ahead with that, right? Okay, cool. Is that okay with everyone if I disable my video for a while? I think there is a slight internet problem. Let's do it this way. Okay. So now let's come back and let us, is it still bad, Arun? Hello, guys. Is the voice still bad? No, right? Okay. Now okay. It was bad. Okay. Cool. Got it. All right. So let's come back on point. What we were discussing is how is attention applied to an RNN, right? We were trying to recall how attention is applied to an RNN. The concept of attention, if you remember, it is a series of 6 steps. The basic idea is to take your key vectors, your query vectors, find the similarity between them, apply a softmax to that similarity score to get something which is known as attention weights. You apply these attention weights on your query vectors to get your final context vector. Does everyone remember these 6 steps of attention? Okay, cool, awesome. So quite a few people remember these 6 steps. Now let us try and recall how we were applying it to an RNN, right? In an RNN, we will take the key as the encoder hidden states. Why the encoder hidden states? Because this is the knowledge that is coming to us, right? This is the input sequence. We have to do something with the sequence using an RNN. So the encoder hidden states become our key. Our query becomes the decoder hidden states, because while we are generating, we want to see what is the relevance of the knowledge base that we have, right? So we will put the query as the decoder hidden states. And finally, the value is also going to be the encoder hidden states, right? If you notice, the key and the value are the same thing, right? So when we say key value are the same thing, right? We've seen this very commonly. Why is the key and the value the same thing? Because we want to calculate what is the relevance of these words within the knowledge base that is given to us, right? So when we have key and value to be the same thing, we're essentially first trying to understand what is the similarity of the text with itself. We are going to get a attention weight with which we can weight the decoder hidden state, so that while the generation is happening, the decoder can use the attention weights to give the final output. Okay. So this is essentially what we're going to see in the first part of the class. Now, before we go here, I just wanted to recap the different types of attention, because this is going to come up a lot, right? So first, let us quickly recap what are the different types of attention. Then we will go to the agenda for today. Okay. So the first type of attention is distinctive and self-attention. Do anyone remember what's the difference between these two types? I'll give you a hint. It has something to do with what are the key values and queries. Does anyone remember what is distinctive attention? Right. Cool. Awesome. So self-attention has key equal to value equal to query, and distinctive is when key and value are the same, but your query is different, right? Query is different. So essentially, this is what your distinctive attention means, right? So in this setup, can you tell me what is, so in the RNN setup, is it self-attention or is it distinctive attention? Which one is it? Very obvious, right? Now that we know the difference. Distinctive. It has to be distinctive, right? Okay, cool. Now let's go to the number of positions. The number of positions is basically has to do with how are you using the softmax to give the final probability, right? So if you remember, soft or global is what we do normally, in the sense that we apply the softmax to the entire vector and give it as the output. In hard attention, what we do is we basically take the maximum probability word and use that as the output of your context vector. So it's like this. In the soft or global attention, your context vector is a linear combination of all the context vectors which are there in the key, right? Sorry, in the query. It's a linear combination of all the states which are coming in your query, whereas in hard attention, it will be just one of them. Okay. Guys, is the voice still bad? Okay. I'm getting mixed responses. Two people are saying, okay, it's breaking at times. I see. Cracking in the middle. Okay, guys, let me do one thing. I'm going to refresh my, yeah. Okay, for Reshma, it's clear. That's interesting. Let's do one thing, guys. Can I request everyone to just refresh their web pages once? I will do it as well. Once we come back, we will just quickly discuss this, right? Just want to do that. I request everyone to refresh. I think there is a problem. I'm going to do it myself now. Hello, guys. Am I audible? Awesome. Okay. Cool. So let's try it now. Okay. If there are breaks from this point on, let's see how to handle that when that time comes. Okay. Let's try for now. Okay. So what we were speaking about before we refreshed our screens is what are the different types of attentions, right? We have distinctive and self-attention. We have soft, global, and local. Soft or global versus hard versus local. So we had seen a difference between these two. Local is just hard attention applied in Windows sizes, right? Okay. So hard is basically when your context vector returned. Okay. Indradeep's question to me is there any specific cases where hard attention is used? Yes, Indradeep. So when we come to transformers, we will see that attention applied in the transformer architecture is very inefficient for very large inputs. Okay. It has a very bad time complexity. So we use hard attention when we want to improve the time complexity performance of our algorithm. And somehow it just works. Like what people saw is, okay, even if you change this one small part, uh, it kind of works. So that's the use case of this hard attention. Okay. Now let's come to number of representations. Single head versus multi-head. So this is something we just discussed. Single head is when you have a single key query value pair. Multi-head is when you have multiple key query value pairs, and all of them are trainable, right? Uh, the major reason why we use multi-headed attention is because we want different components to pay attention to different parts of the sentence. So this improves the performance of your overall network, and that is why we use multi-head attention. Finally, we have attention based on the number of abstractions, right? So single level versus multi-level. Quick example, a single level attention is when you uh, apply attention only on the words. Whereas if you have a very large document and you want to have one attention which works at the word level, another attention which works at the document sentence level, right? That is where you would bring in a multi-level attention component. Okay. So with that out of the way, let us quickly see the agenda for today. Okay. The first thing we're going to do is we're going to see a code implementation of RNN plus attention, right? This is something we have not seen so far. So we're going to see how we implement an RNN with attention. We're going to see a single-headed attention here. Then we're going to discuss the transformer architecture, right? The transformer architecture is something which gets rid of this RNN because the RNN is quite inefficient in certain ways. So what people discovered was you can get rid of this RNN and do everything using just the attention blocks, okay? So we will see different types of attention blocks which comes into this transformer architecture. And finally, we're going to see the implementation of this transformer from scratch using Keras and TensorFlow. Cool. Does that sound good to everyone? Quick yes? Awesome. Okay, cool. So let's get started, guys. So the first thing I'm going to do is first thing I'm going to do is I'm going to take a look at this. So Bishwarup, we won't be able to discuss GPT till we discuss BERT, right? Today the type of architectures we're going to be looking at is encoder and decoder. So to give you a little bit of context, if you have just an encoder, then it's known as BERT. If you have just a decoder, it is a generative pre-trained model, right? So GPT is a variant of a transformer, and BERT is also a variant of transformer. So till we understand this, we can GPT. So I request you to wait till the GPT classes to discuss the GPT library. What we'll be seeing today is how to implement attention with RNNs and how to implement transformers. These two things we'll focus on today. Okay, cool. So let's get started. Let's quickly recollect what was the problem statement, right? The problem statement that we're going to solve through this code is we're trying to find we're trying to do aspect-based sentiment analysis in the sense that I have a lot of reviews from a lot of people. What I basically want to do is I want to take the review string. I want to select one aspect of it. Like for example, let us say there are 300 reviews. I quickly want to see out of those 300 reviews, how many people thought the cost was good, how many people thought the food was good. I can do that if I can specify a query word, right? So something like ambience. This is a query word I can give to this. I can run some statistics on how many people thought the ambience was positive versus how many people thought the ambience was negative, right? So this is essentially what aspect-based sentiment analysis is. And what we're going to do now is we're going to apply an RNN plus attention solution to doing this thing. Okay, cool. So this notebook essentially is something that you've seen before. It essentially contains all the attention concepts that we've seen so far. So let's quickly get down to brass tacks in the sense that let's quickly get down to solving our actual problem. Okay, so let's start here. First, what we're going to do is we're going to get everything, import everything important. The thing which is important to note here is we're using this XML thing over here. Okay, the reason why we're going to be using XML is because our data is encoded in the XML format. We have to use XML library to sort of get things properly, like extract things in the correct way for our application. So we're going to import this one. This code essentially downloads all the data that is required. Okay, And now let us see what is our data loading. Okay. So first of all, what we're trying to give as output is positive, negative, and neutral, right? Essentially, if we input a certain string and an aspect, the output that we're going to expect is going to be one of these three things. So that is why we're going to encode this using numbers. So positive is 0, negative is 1, neutral is 2, and we're going to call this polar IDX. Okay, so this is an index for the outputs that we're going to get. Then you have index polar. So essentially, if we are going the forward direction, we should be able to come the other way, right? Because our neural network is going to give us a number. So this IDX polar is a dictionary which stores the reverse mapping of this. Okay. So we have these two dictionaries. Then we have these two functions, which is parse XML 2014 and parse XML 2016. The reason why we need these two separate parsers is because there was a change in the way XML worked, right? So we have these two separate functions which are able to parse the 2014 version of the XML and 2016 version of the XML library. Okay, so this is essentially just going to help us parse stuff. So now let us see what our data looks like. So we essentially have a lot of data from multiple different sources. So what we're going to do is we're going to try and combine all of this so that our overall training can happen on a combination of these data sets, right? So for example, this one is, I believe 16, right? So this will be in XML 16, this will be in XML 14, this will be in JSON format. So we need to parse all of them and we need to combine them together. So let's quickly do that. So restaurant is basically pd.concat of all of these, right? The axis is going to be 0. Essentially what we have in our data is the sentence, the term is essentially the query term, right? And the polarity, which is negative, positive, and all that. Okay. So this is what our data looks like after we have parsed it and combined it. Okay. What we're going to do is we're going to do a little bit of exploratory data analysis before we go ahead. So we have the data uniqueness. We have 2,243 sentences. We have 938 terms. We have 3 types of polarities, right? So essentially, this is what our data fundamentally looks like. Our polarity is distributed as follows. We have 2,217 positive terms, 899 negative terms, and 126 neutral terms. Do you feel this data set is balanced? No, right? Data set is not balanced. We have to keep this in mind. What is one way to take care of data set imbalance, guys? Something we can do at the loss function stage. Do you guys remember? Focal entropy. Perfect. Yes, we can do a weighted version of our cross entropy where the weight is 1 minus pt to the power gamma, if you remember. That is the focal cross entropy function. So the idea over there is that things which have more representation should have a lower probability value. Things which have a, sorry, my bad. Items which have a lower items which have a lower representation, like neutral over here, right? We should probably increase the weightage associated with this. We should decrease the weightage associated with this. Okay, so that is essentially how we're going to do this. Now let us see what happens after we remove null rows and sentiment label distribution. So as you saw, there were some labels which were null over here, right? We're simply getting rid of those. Once we do that, the number of the distribution of sentiments becomes like this. Okay, 157853886, and this is what we'll be training on, because it doesn't make any sense to use null as our query word, right? It will confuse our model if the aspects are not correct. So that is why we just simply get rid of all the null values and we pre-process our data. Once we do all of that, this is what it looks like. Okay, so if you notice that one null value which is coming here is gone. Okay, so we have done our pre-processing properly now. Now let's move on. Here you have a function which essentially makes things clean, right? So it essentially converts all the spaces to this, essentially, if I understand correctly. And once we're able to do that, we apply our usual pipeline to pre-process our text. Okay, so let's go through this. We are going to do data processing. We're going to encode our labels. We're going to remove punctuations and lowercase the sentence, text, and aspect text. Why is this important? Because of tokenization, right? We essentially want to make sure whatever we work with are tokens, word tokens, and all of these are important steps before we can proceed. Okay, so that is what's being done in this cell. Once we do that, we apply the train test split on our data set. Essentially, we want to make sure we are able to see how training progresses by using the validation data set, and the final accuracy of the model is going to be determined by the test set. Okay, so that is what we're going to do. So this is what it looks like, what our training data looks like after we do the train test split. Now we have 1326 positive, 0, 472 negative, and these many neutral. Okay, so essentially we have this kind of a distribution for a training data set. Now comes the first step before we feed our data into our neural network, right? Of course, we all know this. We spent the first few classes discussing this. The first step is always to convert your words into vectors. We're going to use this word-to-vec model from Google News to do this, okay? And let's see how we are going to use this. So we have decided that our embedding dimension is going to be 300. We're going to use this word-to-vec model, and we're going to embed each of these words, which is there in our sentences, into its corresponding vector. We're going to encode the terms also in terms of their vectors, and we're going to do this, right? Okay. So now let's see how this is done. My num tokens is nothing but len of tokenizer word +1. Why this +1? Can anybody guess? What is the job of this +1? Index. Basically, out of vocabulary, to handle out of vocabulary words, we are essentially going to increase the number of tokens over here. So we're going to have that. We are also going to keep the hits and misses. So once we do that, we have to check whether our word-to-vec has proper embeddings for all the words which are there in our corpus, right? So what we're doing here is essentially we're counting how many words are there, right? So let's sort of go through this. My embedding matrix is np.zeros of num tokens followed by embedding dimensions. So 300, right? So this allows me to essentially find a representation for all my words over here. So this embedding matrix is going to pre-compute all the vectors, embedding vectors for all my words, and then we're going to use this embedding matrix whenever we need it. Okay. So my embedding vector is none. Initially none. What we're going to try is embedding vector equal to word-to-vec of word, right? And in case of an exception, when will the exception occur? Arun's question to me is basically out of vocab words count we are seeing. No. Let's understand this, right, Arun? So yeah, exactly. Not seen in Google News corpus. Let's see how this is working, Arun. Let's focus here. My embedding vector is initially none. I'm going to try applying word-to-vec on this word. If the word is not found, this embedding vector is going to remain in this, right? This embedding vector is going to remain none if this word-to-vec was not able to convert it, okay? So if this word-to-vec is not able to convert it, so for the number of misses that we're seeing here is essentially the number of times this embedding vector stayed none, okay? So essentially now what I have is, I now have an embedding matrix which is going to have 2706 words from my corpus, which are successfully converted, and 205 misses. Okay, so there are some words in my corpus which do not have a word-to-vec. What kind of words can you guess these are? Can these be names of the hotels? Can these be proper nouns? Yeah, they can be, right? So what we're now going to do is for all these misses, we're going to have zeros as the representation. If you think about it, our embedding matrix is np.zeros, right? So whatever did not get encoded successfully over here is going to be encoded with that last out of vocabulary vector. Our last out of vocabulary vector is simply going to be a vector of zeros. That is what our embedding is going to be. Cool? Are we okay with this? Can I proceed? Okay, cool. So let's proceed. Now comes the fun part. Now we're going to see how attention layer is going to be implemented, right? So let's go through this quickly. So my attention is nothing but a subclass of my layer class from Keras. What I'm going to have here are these dense layers. Okay, I have W1, W2, and V. Okay, units over here is essentially the size of the output of my attention vector. Okay. So this units is going to control the size of the output of this attention layer. Okay. The trainable layers we have are these three dense layers. The first two, W1 and W2, have self.units as the output size, and self.v has a output size of 1, right? So you can, so let's see how we are going to use this now. So this is a function which is required. You need to sort of update. So whenever you inherit from this layer class, right, in Keras, you need to redefine this config in a way that the inputs that are there are put over here. Okay. So that is why we're going to do config.update units where it is self.unit. So this is nothing but one of the parameters of your layer, right? So that has to be updated here. This is a necessity. Then we have this call function. Let us see what happens when the call function is there. This is actually the function which is called when we pass an input through this layer, right? So everyone remember what functional API is in Keras? So I hope this is not mysterious when I say that this is the function which is called when we give inputs. Okay, cool. So let's see. Query hidden state shape is batch size comma hidden units. My key shape is batch size, max len, and hidden size. Okay. So what I'm basically now going to do is I'm going to treat the query and the keys differently in my attention layer. Okay. So let us see how these are getting handled. So my query with time axis is essentially going to, so this flag here is controlling, so this flag is something that we have to give to make sure that the query is in the correct dimension which is there, right? So let's see this. What we expect is that this query is of this size, okay? What we want is a query which is this way, right? We know that for this implementation, we are going to have a single query word. So we want our query vector to be of this size. In case it is not this size, then we say flag is false, okay? And if flag is true, then it does nothing to it, right? So if you notice, this expand dims of 1 is simply adding this one dimension over here, okay? So this part is taking care of the shape of the query vector. Now, this is the important part, right? This is the place where our actual attention is getting calculated. Okay. Arun's question to me is call function, please a bit confused. Okay. So Arun, I'll give you a code example. Okay. So if I say layer equal to this, okay, let me say X is a vector of say size 100, right? How do I pass this input X to this layer? Can you tell me, Arun? Do I not do layer of X? Do I not do this? I do this, right? So when I do this, it is this function which is getting called. Clear? Arun, I'm waiting for your response. Is this clear? Essentially, so this is the functional API of Keras, right? Your layer is basically a function. To pass an input through this function, you give it in this form, right? Yeah, attention.call basically is the same. So let me make it this way. Attention, if I do this, attention equal to attention, say 100, okay? I have this input. So now when I do attention of X, right? This is the same as attention dot call of X. Cool? This will give me true. Okay, fine. So let's move on. Okay. So essentially now this is my call function. This is going to be called when I actually pass stuff to it. So let's now see what's happening here. What I need to actually calculate an attention score is the query and the keys, right? Right. So what the first part of this code is doing is it's making sure that the query is in the right dimension that we wanted. Okay, that is what's happening here. Then we're going to calculate our attention score. This is step 3 of our this thing, right? Of our attention mechanism. First one is to set the keys. Second one is to set the values. Then we calculate a score using a similarity thing. So now let us see what this is, right? Guys, from all the alignment functions that we'd seen last class, do you remember? Do you remember that we had one where we use the neural network layer to calculate the alignment. Do you guys remember this? Instead of the dot product. See, the first example of attention we saw, we were using dot product, but then we saw that the alignment function can be replaced by a neural network layer. Do you guys remember this? Am I not audible? Like, I'm not getting any responses. Guys? NN gave good similarity, right? Yes. So now this is what we're using in this attention implementation. Okay, guys? Let's look at this. We have these two dense layers W1, W2, and we have this third dense layer V. So the score is nothing but tf.nn.tan h of self.w1 of query with time access plus self.w2 of keys. Okay. So now if I'm getting a key and a query vector, key and query matrices, sorry, what I'm going to do is I'm going to pass the keys through this W2 matrix. I'm going to pass this query through this W1 matrix. I'm going to apply a tan h as the nonlinearity on this layer. And finally, whatever I get out of this, I'm going to convert it to a single value to get the attention score, right? This is the final attention score has to be a single number, right? So to get a single number, we are passing it finally through this dense layer called V. So my attention weight comes from this score simply by applying a softmax on it, right? And my context vector is nothing but my attention weights into keys, right? This is the final step of our attention. So this is how I'm creating my context vector. And this attention layer that we have now defined is going to return the context vector and the attention weights, okay? So are you now convinced that this is a implementation of single head attention? Is everyone clear on this? How this is implementing single head attention? Okay. If you're clear on this, we can move on, right? Okay. So let's move on. Now that we have a single head attention layer, we can use this within an RNN, right? So let's quickly define our RNN architecture, and then we will see how we will use this attention to improve the score of this RNN, okay? So my embedding layer is now this embedding, okay? We all know what this is, but there is something special which is happening here. I'm setting this embedding layer to be false. I'm not going to allow my model to train this embedding. Embedding's initializer is nothing but a constant initialization on top of this embedding matrix, right? So this embedding matrix that we have created here is actually coming as the embedding layer in this part, okay? Cool. So we have fixed our embedding. So I kept telling you before, right, guys, that there are multiple ways to get embeddings. This is how you actually implement the constant version, where you simply take word-to-vec weights, pre-trained word-to-vec weights, you make them as false, okay? And then you use this as your embedding. So this is how this is done, okay? Now my review input is going to be an input of shape 20. Why 20? Because I want to fix the maximum length of this. Okay, I want to fix the maximum length of my reviews. So this is the review input text. My aspect input is going to be of shape 2. So at max, I'm going to allow you to tell me, I'm allowing you to use 2 words to encode the aspect over here. Okay, so this is the review input. This is the aspect input. The review embedding is simply passing the review input through this embedding layer. Aspect embeddings is nothing but passing this aspect input through this embedding layer. Once we do that, this is where our RNN implementation begins. Okay, so we have this tf.keras.layers.gru. This is the gated recurrent unit. So what we're using here is not the standard RNN, but a gated recurrent unit, right? Can you guys quickly remind me how many hidden states does a GRU have? 1 or 2? 1, right? Okay. So thank you. This is kind of important. Let's do this now. So the 64 over here tells me that the hidden state size is going to be 64. Return sequence is equal to true is going to make sure that it's not only returning the final output, but also all the hidden states that it is getting, right? And return state equal to true is the last hidden state. Okay, so this is what I'm going to use to encode my aspect. Then I'm going to create another GRU. Guys, I apologize for the misnaming. It is called an LSTM here, but what we have actually used is GRU. Okay, so I did not bother changing this because it's only used in this cell. I just wanted to point out that whatever we're calling LSTM here is still a GRU. The size of the hidden state is still 64. We're making this return all the sequences and the states. Okay. And finally, the whole sequence output is going to be LSTM, that is the second GRU of the review embeddings. Cool. Okay. So we have now one GRU which is taking care of the input text. We have one GRU which is taking care of the aspect. Let us see how we will merge these two to finally build our overall architecture. So my context vector and attention weights are nothing but attention with 128 as the units over here, right? So the units over here is controlling what is the dimension of these key and query vectors over here, right? So I'm now defining an attention layer with 128 as the number of units. I'm passing the aspect as my what was the first one? I'm passing the aspect as my query, and as my keys I'm passing the review, right? Whole segment output is nothing but the hidden states associated with my review embeddings. So this is exactly like we discussed last class. I'm going to treat my aspect as the query vector. I'm going to treat my input review as my key vector. And this is what I'm going to get over here. The context vector and attention weights I'm going to get as the output. Then what I'm going to do is I'm going to create a dense layer. Okay. This dense layer has 64 again as the output. The activation is the scaled ReLU unit. So just quickly want to show you what this looks like. So typically what ReLU looks like is this, right? Our typical ReLU will look like this. Oh, sorry, my bad. The SELU will look like this. Okay, so there are two parts over here. First of all, it is going to allow, so this is SELU, this is my RELU. So restricted linear unit does not pass any negative gradients, right? And the slope over here is 1, if you guys remember. What's different about this SELU unit is it allows some negative gradients to flow through, okay? And the weightage on the positive side is more than the weightage 1, right? Yeah. So there is leaky ReLU. So be sure of the difference between leaky ReLU and SELU is this. Your leaky ReLU will look like this, okay? Your leaky ReLU will look like this. The slope over here is going to be 1, but the SELU is going to have more weightage on the positive side. Okay, so that's the basic difference. Why is this necessary? Because we want to make sure even if something negative is happening, we are able to back propagate it, right? We're able to back propagate it. So this is why we made this design choice over here. Okay, moving on. Now I'm going to take this context vector and I'm going to pass this dense con on this context vector. Okay. Yes. So Indradeep's question to me is SELU a variation of exponential linear unit? Yes, it is. Yes, it is. Scaled exponential linear unit is what I believe it's called. You can check this out, right? Just one moment. Yeah, this is the scaled exponential linear unit. So why isn't this working? Okay, just one moment. It will load. So let's go here. Okay, fine. Yeah, so this is what your ReLU looks like. Your SELU looks like this, right? Two parts. First, there's going to be a negative gradient, and then the scale of this is going to be different, right? Okay. Coming back, let's come back. Now my dense con is going to be a dense layer which is operating on my context vector. My dropout is essentially applied to this dense con unit. So I'm applying my dropout only on the output of my dense con layer. My dense output is going to be the output after I take this dropout output and pass it through this, right? And my final output is going to be a softmax, okay? Softmax with 3 outputs on this final dense output, right? Can you guys tell me quickly why 3? Any reason for using this 3 over here? 3 polarities, right? Perfect. So this ensures that we are now getting a probability on the 3 polarities that are there in our data set. Okay. So this is how we are finally building our RNN architecture. So now my model is going to be tf.keras.model, where my inputs are my review and aspect inputs, and my outputs is this output layer. Okay, cool. Now let us see how we are training. Okay, this is training and validation set preparation. So let's kind of ignore this. We kind of know what's going to happen here, right? The main thing that's going to happen here is they're simply going to take the sequences, they're going to pad it, and they're going to convert it to categorical, right? That is essentially what's happening here. So we can skip this part. Now, once we've built our model, let us see what our model summary looks like. Okay. So this is going to show us our model summary. Before that, we're going to just see how we have prepared our model for training, right? We're going to be using the categorical cross entropy loss with the Adam optimizer with accuracy as the metric. Okay. We are going to save our model from time to time into this file. Okay. Aspect based essay. We're going to save our model here. We're going to save weights only, and we're going to only save the best version of this. Okay. So we are not going to keep saving at every iteration. We're just going to save the best one over here. This is the early stopping callback. What this will do is, if your accuracy is plateauing, then it will stop training over there. Okay. So finally, our model looks like this. You have the aspect input, you have the review input, you have the embedding layers, you have this GRU4, which is going to take care of the aspect. You have this GRU5, which is going to take care of the review. You're going to have this attention model, which is working on the outputs of GRU5. You have this dense, dropout, dense architecture, which is going to work on the outputs of this GRU. Okay. So this is what our attention plus RNN architecture looks like. Any doubts so far, guys? I'm going to pause here before I show you how training went and discuss the results. But any doubts with the architecture at this point? Any doubts with implementation? No? Okay. Guys, have I put the class to sleep? Please respond, right? Okay. 3 people feel like, okay, that there's no doubts. Indradeep has a doubt. Let me quickly address that. In the attention layer, we have 3 trainable matrices, right? Yes, Indradeep, we have 3 trainable matrices. The first matrix operates on the query. The second matrix operates on the keys. The third one converts both of them into a single attention weight, right? That is the 3 trainable matrices we have. Attention won't be passed to further layers. Anil, no, it won't be passed to further layers. Attention is only being used on the RNN output. So if you are confused about this, please look at last class's diagram. Okay, so I'd made it quite clear how we're applying attention over there. So if this is the confusing part, please check there. If not, I can address it at the end of the class. So you can put up a question on the questions tab for that revision. Okay, cool. So now that we're confident on our architecture, let's go ahead and train. Okay. So training is going to be pretty straightforward, right? We are going to apply some sort of oversampling over here. So guys, we selected our loss function as categorical cross entropy, right? We selected our loss function as categorical cross entropy. Let me just go there. So we have actually not used focal cross entropy here. So to actually avoid the problem of imbalanced data set, what we're going to do is we're going to oversample our we're essentially going to oversample our things at the this stage, right? Let me just go there. Sorry. So we have actually taken care of the oversampling over here. Okay, so when we're preparing a train, test, and validation sets, we have made sure that things are sampled properly over here. Okay, so we have not handled the imbalance by changing the loss function. We've handled it by oversampling over here. Okay, cool. Now let us see how training proceeds here. Okay, we set up training for 300 epochs with a batch size of 64. Our validation data is what we're passing here, and we have set our callbacks over here. So ideally, this should run for 300 epochs. Let us see how many epochs it actually ran for. So it turns out that after 22 epochs, we can actually do an early stopping over here because the training loss saturated, right? The training accuracy saturated. So because the training accuracy saturated, we stop at 22 epochs. And this is what our training and validation this thing accuracies look like. Can you guys tell me, is this a case of overfitting or underfitting? It's a case of overfitting, right? It is not able to perform that well on my test set, but it's doing quite well on my training set. Okay. How to fix this, we will discuss in a short while, but the results that we get are kind of encouraging. So what we're going to do is we're going to simply take this model, see what the results look like, and later on we will see how to improve this. Okay, cool. So now my model dot, I'm loading my saved model over here. I have my label maps over here, right? So what I'm going to do is now I'm going to take an input string. I'm going to take some aspects and we're going to see what the output is for this sentence. Okay. So the service was worse, but ambience was amazing. So if I use service as my aspect word, what is the sentiment over here? Is it negative? Is the sentiment with ambience positive? Okay, cool. So let's see. So now all of this code is essentially passing this input sentence and ambience and service as the aspects. Let us see what we get. Okay. So when I take this sentence and I pass ambience as the aspect, the output I get is positive. Okay. When I give service as the term, the aspect is negative. Okay. And what's nice is we can exactly figure out why this happened. We can exactly figure out why this happened. We can actually break open our attention layer and see the attention weights to see what was happening here, right? So let us quickly visualize why it decided this. So it turns out that when I'm plotting this sentence with the aspect term as service, the attention that the most attention paid is on this word worst over here. Okay. Why is it worst? Because it is associated with the word service, right? So to some extent, we have managed to train a model which is correctly picking out correctly paying attention to the right word associated with this input aspect, right? So this is how we have a very nice interpretable model. So if we now give a different review to this and ask for a different aspect, and it does not give us the correct answer, we can actually break this attention layer open, see why it did not give the correct answer, and debug this, right? Isn't this awesome? For the first time, we have come across an architecture which is telling us why it is screwing up, right? The attention weights is what will tell us why it's screwed up. So we have a nice interpretable model now, okay? LSTM, yeah, explainability is quite nice here. So that is one of the really nice things about attention. It gives us explainable ideas, okay? So now if I do the same thing, so here I had given the aspect as service, it picked worst as the maximum word. When I give ambience as the word, it picks amazing as the maximum attended word. So it's able to do both of these things in this attention layer, right? Okay. So now I just want to show you a quick comparison of how much attention helped us improve the performance of this LSTM. So let us say we did not use the attention layer, okay? What we did was we basically trained a model where we did not apply the attention layer. We simply asked the final outputs of that to generate the word. If we do that, the accuracy that we get is 72%, whereas LSTM plus attention gives us 84% accuracy. So what I want you guys to notice here is the attention mechanism is very, very powerful. Okay, this is an order of magnitude improvement. From 72%, it took it to 84%, right? So in that sense, attention plus RNN is a much better way of doing things than simply using LSTMs. Okay, so that's the main takeaway from this. That's the main takeaway from this. Now what we're going to do is we're going to switch our attention to understanding what transformers are. Okay, cool. So let us switch gears. Let us quickly dive deep into what transformers are. Let us quickly understand how the transformer architecture works. Once we have understood that, we're going to see how to implement that architecture, right? Okay, cool. So let's start our discussion on transformers. In the meantime, does anyone have any doubts up to this point? Are we okay with the results? Are we convinced that attention is very powerful and it's explainable? Are we convinced? Okay, cool, cool. So now what we're going to do is we're going to put even more faith in this mechanism. We're going to say, okay, my RNN with attention did so much better, but do I really need that RNN part, right? Do I really need that RNN part? Can I do everything with just attention mechanisms? What are the challenges that we will face? How are we going to deal with the challenges? All of that discussion is now going to happen. Okay, cool. But so Anil's question to me is, do we call this interpretable or explainable? Anil, the difference between interpretable and explainable is explainable analyzes the outputs, right? Interpretable analyzes the inner layers. So explainable, we say attention in this context is explainable and not interpretable, because we have not put our attention at the last, in the middle, right? We have applied it to the last layer. The attention output is what is directly getting converted. Okay, why is it explainable? How is it interpretable? So we say that okay, let me put it this way. LSTM plus attention is explainable, whereas LSTM is not explainable. Let us understand why. LSTM plus attention, if my final answer is wrong, I can look at these attention weights and figure out why it went wrong. Okay, right? So what do I mean by explainability? If my model gives me the wrong answer, so in explainability, we're treating the model as a black box. If my model gives me a wrong answer, can I tell why it is giving the wrong answer? The answer to that question is explainability. Okay. The fundamental definition of explainable in the literature is, can I analyze at a black box level why my model is giving me the wrong answer? Okay. Do you guys remember computer vision GradCam? Can you say that the model was explainable over there? If I apply GradCam on any convolutional neural network, does that make my model explainable? Yes or no? It does. So this is what explainability means. Interpretability is one level above that. Why? Because in interpretability, we have to break open the black box. When do we say a neural network is interpretable? When I can justify from starting to ending what is happening at each step. Okay. So for example, if we crack open a neural network, if you guys remember, I had shown you a CNN explainer website. Do you guys remember that? CNN explainer website? Okay. So in the CNN explainer website, if you remember, it was very clear what was happening in each of those feature maps, right? If I can explain what this model is doing at each of the feature maps level, then I say my model is interpretable. Okay. So that's the fundamental difference between interpretability and explainability. In explainability, I don't open the black box. In interpretability, I have to open the black box and explain it. Okay. So are we now clear on why this is explainable? Okay, awesome. Perfect. So now let us use this explainable idea of attention exclusively to see what's going to happen. Okay, to solve a problem. Okay. Anyone have any other doubts before I start the Transformers content, guys? Anyone? If you do, please ask me now, right? Before I move on to Transformers, if you have any doubts about single-headed attention, how it is improving RNN performance, any of those kinds of questions, you can ask me now. If not, let's move on. Okay. Does anyone want a break at this point? Okay. 3 people want a break, 2 people don't. I'll wait for the people to respond. In the meantime, I handle Indradeep's question. Why did our previous model overfit? We had a small data set and large number of parameters. So the main reason why it overfit is because our data is small, Indradeep. My debug on this is that the data size is too small for it to generalize, right? Whenever you have overfitting, it means your model is not generalizing. It has not seen enough examples to generalize. So that's my debug on this. I don't think it's a problem with the model itself. I think the number of parameters we have are kind of small only. So yeah, I don't think there is any way for us to reduce this, right? So my debug is not enough data. Cool. So people want break. Let's do one thing. Let me set a timer. Oh, my bad. Just one moment. Where did this disappear? Okay, perfect. So what I'm going to do is I'm going to introduce the problem statement that we're trying to solve, right? I'm going to first introduce the problem statement. Once we do that, we will take a break. Okay, one moment. Mayur's comment is, to absorb everything for me, it takes 2 to 3 more revisions of one class. This weekend, I got to know what transfer learning is. Oh, okay. Mayur, I'll tell you one thing. It is okay to be slow. See, everyone learns at different speeds because, and the reason why we learn at different speeds is because we have different backgrounds, right? I'm I'm sincerely happy that you're taking the time to revise two, three times and understand these concepts. That is in itself very commendable. Okay. My suggestion to you is this: you may be slower than other people today, but if you keep this hard work up, someday you will catch up. And if you keep that up, even when they are snoozing, right, you will overtake them. So, what I'll suggest is this: uh, please keep it up. Please keep it up. Please keep revising. If you have any doubts, if you have any parts which you're not understanding, please get in touch with me. I'm available on Slack and I don't mind talking about it. Oh, okay. But I know VGG and all since 2019. I see. So where is the gap? Oh, okay. So I want to try and understand the gap if that's okay with you. Ajay says it's the fourth time someone teaches me attention. Now I can relate. Ha, okay. And there's one more thing, guys. So Mayur and Ajay, there is one thing that I want to point out to both of you. These are research level subjects. Nobody on earth understands them at the level we understand polynomials and integration and differentiation. Okay. These concepts, polynomials, differentiation, integration, these mathematical concepts have had hundreds of years to grow into the clarity we got today, right? What both of you are witnessing right now is a revolution where we are discovering new things and we're communicating them to other people at top speed. Okay. One thing you have to change in your mentality is understanding something is not understanding it completely. Understanding something is, can I use this? Can I take this concept, apply it, and use it to solve my own problem? So the definition changes. Okay. So what I would suggest to you is what I would suggest to you is this: if you are feeling like you're not able to understand something, that's a very normal thing because of how these topics are. These are research topics, these are not straightforward things. So, this is something which does require that amount of discipline, right? So, I'll sit today, I'll read a paper on computer vision. Tomorrow, something else will come which is better than this and which will point out mistakes here. I have to be mentally prepared for this, right? So, Mayur, when you read VGG and all in 2019, the state of the literature was different. Today in 23, when we're sitting and studying these concepts, state of the literature is different. Back then, people thought VGG is the best module. Today, people know efficient net is way better, right? So that is what I'm trying to tell you. This is an evolving field, and you have to set your expectations clearly. So yeah, that's my counter to this. Cool. So I think that was enough of a break for people. Yeah. Hmm. So yeah. Indradeep's question is, thank you for comment is, thank you for explaining difference between interpretable and explainable. Okay, you're welcome. Uh, yeah. Okay. So guys, I'm getting a lot of questions right now. Let's do one thing. I'm going to start the break. If I take any longer to address your questions now, we're not going to be able to finish on time. So my request to people is, so people who have asked me questions in private chat, right, guys, please, I request you, your questions are common. Okay. Other people will also have these doubts. Please put it up on the questions tab. I will address them there. For now, let us start the break. Once we come back from the break, let's discuss transformers. Once we have understood transformers to a good enough level, I will address your concerns, right? Let's do it properly. I'll see you guys after the break. And we're back. Can I get a quick confirmation if you guys are back? Some people are not back. Okay. Cool. 4 people are back at least. Okay. 6 people are back. Awesome. Awesome. Okay. So, guys, I think it's kind of important for me to address this problem right now. Anindya's question is quite valid. And I understand that when we are dealing with tough topics, right, it feels like we don't understand anything. So let me deal with this right now. Okay. Anindya's question here. Okay, guys, I'm going to switch off my audio. I think there's going to be a internet issue. So yeah, I'm going to switch off my video. Yeah, of time to understand that. I want to remind you guys of something. Okay, this one implementation, this one architecture implementation that we saw just now, it has used concepts from every part of the scalar course. Can you guys tell me? Can you guys tell me if you did not know object-oriented programming, right? If you did not know object-oriented programming, would you have been able to understand this attention layer? Okay, Arun says no. Okay, you would not have been, right? So what I'm trying to tell you guys is the reason why we put NLP and CV at the end is because when it comes to research level topics, your base has to be very strong. Okay. If you did not know, if you did not go through the Python module, you would not have been able to understand this implementation of the attention layer. Okay. If you did not know probability and statistics, you would not have been able to understand what the softmax means. You would not be able to understand what probability means. If we did not teach you pandas and numpy, you would not be able to understand how to deal with data frames, how to pre-process data, how to do all of that. If we had not gone through math for ML and linear algebra, all of these neural network concepts would not have made sense. If you had not gone through the uh, neural networks module, you would not have known Keras. What I'm trying to remind you guys is the reason why these topics, these research level topics are coming at the end is because we believe by now we have equipped you with enough uh, base, right? We have equipped you with enough basic concepts that you can go out there, you can read these research papers on your own and implement them on your own. That is our expectation from the excellent students who are there, who have been going throughout the scalar course. And I have met enough excellent students, okay, who have used every aspect of the scalar course to come to these research level topics. If you are struggling over here, it means that you went wrong somewhere in the earlier modules, okay? If you are finding this kind of discussion difficult, it's because you were not able to understand or grasp things from the earlier modules. So when it comes to research level topics, even in a PhD program, what the professors do is they teach you the basics and they throw you out, right? They throw you out into the world to read and implement research topics. Anindya saying he doesn't agree with me. Anindya, please let me know. What are your thoughts? I'll be more than happy to address them, right? Have I, okay, please explain. What could we have done better? And guys, since this discussion has come in the middle of a class, I'm really sorry. I cannot help it, but we will have to take more time to cover the transformers concept. I have to finish this today. This is just a warning for everyone. We are going to take some extra time today. Okay. In the meantime, Anindya, if you would be happy, I would be happy if you unmuted yourself and told me what your concerns are. I would like to understand what we could do better, because if you have better thoughts, I think the entire research systems of the world can be improved through your suggestions. Please tell me, what are your thoughts? If you don't agree with me, please explain. Why don't you agree with me? How many people feel okay? Fine. Okay. Yeah, Anindya, please go ahead. I have unmuted you.
Can you hear me?
Okay. I'm not able to hear you, Anindya, yet.
Hello. Can you hear me?
Sure. So Anil's request is we take this at the end. Anindya, let's do one thing. Let's take this up at the end. Uh, what we can do is I'm going to mark your question as answered for now. I'm not able to hear you, so please check your microphone connection. What we can do is at the end of this class, we can discuss philosophy. For now, let us go understand what transformers are, because that is one stepping stone to understanding GPT, right? My sincere request is please stay till the end of the class because I want to understand what we could have done better. Okay, cool. So for now, guys, let's resume our discussion of the transformers concept. Okay. So the problem we're going to try and solve using transformers is the machine translation problem, right? It's a straightforward problem. If I'm given a sentence in Portuguese, I'm expected to produce the translated version in English, right? Is the problem statement clear to everyone? Given sentences in one language, we have to translate it to another language. Okay. Now, essentially, problems which take a sequence as an input and problems which give a sequence as an output, right? These kinds of problems are known as sequence to sequence learning algorithms. Okay, we've come across a lot of these so far. Text summarization is an example. This machine translation itself is an example. Parts of speech tagging is an example. Yes. So sequence to sequence learning algorithms are types of algorithms where input and outputs are sequences. The question is, how have these evolved over the last so many years, right? So at the beginning, we had rule-based systems where essentially we have specific rules which help us translate sentences from one language to another, right? So 1950s was the era of the Cold War. If you know, Russia and US had like spies going all over the place. They were trying to steal each other's secrets and all that, right? So at that time, it was very important for them to come up with models which could automatically translate Russian text to English, right? Enigma was in the World War era. So Enigma was a machine which translated German code. Okay, so Enigma was something else, right, Arun? It took German codes and decrypted them. That was in, yeah. No. The problem is also different there. There we had an encrypted algorithm. The language was not straightforward, right? It was numbers. You had to do something to those numbers to convert it to text. So that is totally different. When it comes to translation, we already know the rules of one language and the other language, right? We already know these two rules. So when it comes to rule-based rule-based models, we used to have this bilingual dictionary to map Russian words to English words wherever things. So we did not care about the sequence over there, right? We did not care about forming meaningful sentences. We simply did one-to-one mapping between Russian and English words, and we applied a rule-based system to do translations. In 1990s, people started using statistical models like those which took statistical models like the what do you say, the naive Bayes classifier, right? That is a statistical model. So they started working on bigram, trigram, like all the concepts that we've studied earlier in this course, right? In the NLP module, that is what they picked up, and they built models using that. And finally, after the 2010 era, we started using neural networks to do this translation task. So you have sequence to sequence types of models. You have sequence to sequence with attention. This is nothing but the RNN that we saw, right? And then we have transformers, which is the latest development in this type of networks. So let us quickly run through how each of these would work. In a rule-based machine translation system, you would first get the parts of speech tag for each of these words. You would get syntactic information about these verbs, right? You would take objects of the verb. Like every verb in a sentence has to be associated with a noun because actions have to be associated with objects, right? So we have that level of parsing which is happening here. And finally, the translation is happening using all of these three things which are okay. So for example, you have a girl eats an apple becomes this, which I cannot pronounce. I'm sorry. I don't know enough German to pronounce these, but this is how the translations essentially happened, right? Okay. The advantage is this was very fast to do and it was quite deterministic. The disadvantage is manual dictionary creation, manual linguistic rules creation, and more the rules, the harder the system is to deal with. So people had to actually sit down and create these things, right? In this era. So this was quite painful. So then what people started doing was they started using probability to essentially to do the translation. So here the example is we are taking an English sentence and we're translating it into Chinese. So he goes to the curry restaurant, becomes this. And then different probabilities associated with these sequence allows us to resequence this, right? And you can imagine how a probability-based model works over here, okay? And finally, in today's era, we use neural machine translation, right? So the RNNs that we have seen so far is an example of neural machine translation. In fact, the first attention paper which came out in the literature was on neural machine translation. So those people essentially wrote a program to translate, okay, not Portuguese. I forgot which languages they were using, but they wrote a program to use attention mechanisms to do machine translation, and that was widely successful. So the same thing was done by the transformers people. So the transformer paper actually uses only attention mechanisms to build a model which can translate Portuguese sentences to English sentences. That is how that works. Okay. So what we're going to study today is the evolution of neural machine translation. So we started off with RNNs, then we learned LSTMs and GRUs, and finally now today we saw code for RNNs plus attention. So what we're going to do now is we're going to see if we can get rid of the RNN part and only use attention mechanisms to do the whole thing, right? Okay. So this is like a quick comparison of each of these things, right? The pros and cons are listed here. Specifically, let's see the pros and cons of neural machine translation. So the pros of neural machine translation is it can produce more natural sentences and higher translation quality than the previous two. The con is it takes time to learn target data, right? Yeah. The con is that it takes time to learn target data. So this is essentially how the state, like these are the different types of methods we can apply to do machine translation. The quality versus progress graph looks like this, right? So in 1954, we have Georgetown, ALPAC, Meteo. These are all rule-based systems which were developed at different points to translate languages to English. Then at this point, we started having this, right? We started having statistical machine learning approaches. And finally, in 2010, roughly, had neural networks which are enabled translation. Okay, history looked. So far, neural machines mainly been based on an LSTM mechanism. So this is sequence to sequence, which essentially takes the input sequence. It stores a certain memory location, which it passes to the decoder. And finally, the decoder uses this intermediate representation to give the predicted sequence. Okay. 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 Bad connection, lot of breaking in the middle. Guys, can you just give me 1 second? I'll quickly refresh and come back. Okay, guys, I'm back. Apologize for the voice breaks. Is this better? Okay, this is better. Okay, all right. So let's continue with this discussion. Here we have an encoder-decoder architecture, right? Here we have an encoder-decoder architecture. Essentially, we have the input sequence, the intermediate representation, and the predicted sequence. We are not new to this. All of RNN and LSTM discussions were based on architectures which look like this. Okay. Now comes the question of how are we going to build an encoder-decoder architecture using just attention mechanisms? That is the challenge, right? For today, we have to only use attention mechanisms to get the encoder-decoder parts. So let us discuss how we can go ahead with this. Okay. So this is essentially an overview of how a machine translating algorithm or how a machine translating neural network would work. The RNN would essentially take all of these tokens. So you have the start token, I love learning end token. We would have 5 hidden states over here. This is now passed to a context vector. So this will generate essentially a hidden state, which is then passed to your decoder. And the decoder will finally give the translated output over here, right? This is what an encoder-decoder architecture with an RNN would look like if we used this to solve the machine translation problem. Question is, what are the issues with this, right? Bottleneck problem and parallelization. So the bottleneck problem is what we discussed a little bit last class. The bottleneck problem is there is a single state over here which has to take all the information, right? And we saw how to fix that with attention just now. The other problem which we have not yet discussed with LSTMs, RNNs, GRUs, right, is that they're not parallelizable. Why are they not parallelizable? Let us understand this quickly. Okay. The basic problem over here is this. Until I calculate hidden state 1 and 2, I cannot actually calculate hidden state 3, right? So this is some sort of a sequential operation. I cannot actually break down this model, ask server 1 to compute this, server 2 to compute this, server 3 to compute this, and so on, right? So by default, the RNN architecture is not parallelizable. Okay, it's not parallelizable. So if you know a little bit of computer science, you know that the basic need for parallelization is if your model is parallelizable, you can train huge models. The size of the model can increase, the time it takes to train that model can increase. A lot of good things come out of being able to parallelize stuff. So one of the major issues why we cannot scale up RNN networks is that they have a sequential dependency. Until the encoder executes, I cannot execute the decoder. Do you agree with this statement? Yes or no? Until I go through this, I cannot do this, right? So that is why inherently recurrent neural networks are not parallelizable. Okay, that's the issue. So we solved this problem by doing the following, right? We saw an example, code example of this just now. We have the encoder. We take all the hidden states of the encoder and we pass it to a attention / context state over here. Okay. The output of this is passed as it is to the decoder, but the input to these decoders is nothing but the context or attention weighted things that are coming here, right? So the input that we feed to the decoder is this context vector that is coming out of this attention module, right? And that is how we're getting this whole architecture, right? Okay. So we have already seen this in detail. I'm not going to spend time on this. I'm going to move on to a quick discussion of now what do we have to do so that we don't have this recurrent neural network and we only use attention blocks to achieve our target. Okay, so let us quickly jump into the discussion of transformer architectures. By the way, guys, all this text that I'm skipping is stuff that I have discussed in the last class. These notes are kind of nice. They revise attention mechanisms again and they sort of fit it into a discussion. So if you're interested, this will be really useful when you're revising, right? So this has been written with revision in mind. So I'm going to skip the parts which we have already discussed. So this is a diagram of the same thing in detail where you have a bidirectional RNN and you have an attention module sitting here. This is something we discussed in detail last class. So I'm going to be skipping this. Okay, cool. So now comes the question of how do we build a neural network using only attention mechanisms? Okay. And the answer to this question lies in something which is known as a transformer. Okay. So a transformer is basically a neural network which has an encoder-decoder architecture. What does this basically mean? It means that I will still have two parts in my neural network. Okay. One part will be still be responsible for making sense of my input sequence. Whatever the encoder learns will be passed to this decoder, and then the decoder has to make use of the encoder outputs to predict the final sequence, right? This is how this whole thing works end to end. So we are not going to go away from this encoder decoder architecture. We're still going to use encoder decoder architecture. Only thing is inside this black box, instead of using an RNN sitting there, we are going to use an attention block. Here also we're going to use attention blocks to solve this problem, right? Okay. So let's keep this in mind and continue. Okay. So let's move on. Broadly speaking, let us see what are the differences between the RNN LSTMs, the RNN LSTM plus attention and transformers, because now we have seen examples of these two, right? So let us now from this table try and understand what is different in a transformer architecture. So first of all, are there recurrence blocks in RNN LSTM and RNN LSTM plus attention? Yes, but transformer will not have this. This is the major difference here. Okay. Okay, so before I move on, there's a very nice question which Bishwarup has asked me. His question is, why do we stick to the encoder-decoder paradigm Because Bishwarup, it helps us keep the two tasks separate, right? So for example, I can use the same encoder architecture to solve different tasks by simply replacing the decoder, right? So that is one very nice thing which allows me to apply transfer learning on NLP networks. So that is why I kept telling throughout this course that transformers are the first time we can actually use transfer learning, right? This encoder decoder architecture helps us apply transfer learning. Yeah, reusability is one of the advantages over here. So let's discuss that when it comes. Okay. For now, let us understand at a block level what is different. Attention is obviously there in transformers. That is all that is there. Context vectors are created using attention mechanisms. Attention alignment functions over here in RNN LSTM, we saw dot product and we saw the neural network version today, right? In today's example. But here, the first few papers of RNN LSTM simply use dot product, and the first paper of transformers used scale dot product. So we're going to use, so think of this as the alignment function that we're going to use today. Okay. The type of attention is fundamentally going to change. With RNNs and LSTMs, because of that constraint, right, of getting only one set of hidden states, we used single-headed attention there. But now with transformers, we have the flexibility of using multi-headed attention. We don't just have to have one layer which is computing attention weights. We can have so many of them, and together they will tell us the final meaning of the sentence, right? So this is the advantage of using a transformer architecture. And finally, RNNs and LSTMs with RNN/LSTMs with attention are both sequential models. This is parallel. So these are the main advantages of the transformer. Okay, cool. So now let us quickly understand what are the different components which go into a transformer architecture. These are the names of the components. These will make more sense if I first show you what a transformer looks like, right? So first we're going to go and we're going to see an overview of what a transformer looks like. Then step by step, we're going to see how each of these is going to be implemented. Okay. So first, let us focus on this part. Let's focus on this part. All right. All right. So let's get this transformer architecture here and let us see what are the different components which are going to come in this architecture. Right? Okay. Cool. So let's trace this first. Let us try and understand, let us figure out what we don't understand and let's focus on it that way, right? Okay. So my inputs are going in over here at this layer, right? My inputs are going in over here. These are my inputs. Once I have an input, right, these are essentially going to be sentences. So in the neural machine translation problem, what is my input going to be? It is going to be a Portuguese sentence, right? Think of this as a sentence in Portuguese. Okay, this is a sentence in Portuguese. Of course, these are going to be words. What do I have to first do before I can send it to a neural network? I have to vectorize this. So I'm going to now pass my inputs into this input embedding part. Okay, input embedding part. And then we come to this very mysterious looking thing over here, right? This is a very mysterious looking thing over here. This is known as the positional encoding block. Okay, so let us quickly discuss why this is necessary. Guys, in an RNN, did I have to worry about sequence, giving a sequence number to my sentences, to the words in my sentences? I did not have to worry, right? Why? Because for every input, because of that linear kind of structure, because of that sequential structure, right? The hidden states used to encode what that word means in that sentence, right? It's that which is determining that. Now, when I'm going to get rid of all the RNN structure out of my neural network, don't you think I have lost all the positional information? So don't you think we have to tackle that somehow, right? We have to tackle that problem somehow. I now have words of this Portuguese sentence, but there is no way for me to tell my neural network what is the position of the word in each of these in this sentence. Okay. So to solve for that problem, we do something which is known as positional encoding. So let us discuss this piece first. How do we now communicate to our neural network what word has what position in our sentence? Okay. To be very frank with you, back in 2009, like when Transformers first came, right? The attention is all you need paper. This was back in 2017. So back in 2017, people thought that positional encoding was a very important step. But in 2021, there was a paper which said that no, we don't even need to do this. The neural network can automatically learn this if we put a deep dense layer over here, right? So that discovery was made quite recently. So this is what I mean by research evolves, right? A concept which was thought important in 2017 is now these days getting replaced with something better. Okay, just wanted to point that out. For now, let us understand how the first transformer model used positional encoding to perform all of this, right? Let's do that. So let's go here. Okay, first, actually guys, I want this from you. Okay, let us say I have this sentence. This is a cat. Okay, this is a cat is my sentence. This word has the 0th index, is has index number 1, has index number 2, and cat has index number 3. Okay, this is what my sentence essentially looks like. What is the obvious way of doing this positional encoding? What is the obvious way of doing this? Add the word indexes and the word vector representation. Okay, that is one way to do it. So it's interesting that Indradeep, you went directly to adding, right? Anil's is a little bit more, right? So these are nothing but the indices associated with each of these words, right? These are the indices. So this is the naive version of this, right? Now, one obvious way is I can simply take these word to vex. So first what I'm going to do is I'm going to convert this word to vex. So I'm going to convert this to a vector form. I'm going to convert this to a vector form, right? I'm going to convert this to a vector form, and I'm going to convert this to a vector form. Then what I can do is I can take this index vectors, okay, and I can add 0 to all the numbers over here. This is what Indradeep was suggesting. Another way to do this is, can I not simply concatenate this over here? Can I not simply concatenate this over here to this? That will tell it in what order it should see these words, right? That is one more way of doing that. But concatenating is actually bad because what you have to understand about vectors and matrices is each entry in the vector or matrices is treated as an independent entry, right? Because of that problem, because of the independence problem, concatenating is not an option. And what people saw is that it's better to add this to our vector, okay? Which is why Indradeep is suggesting adding, right? Okay. So just wanted to discuss why concatenation is not an option. So now what we can do is we can simply take these indices. To this word to vec, I'm going to add the value 0. To this, I'm going to add value 1. To this, I'm going to add value 2. This, I'm going to add value 3. Can anybody in class tell me why this is a bad idea? Why is this a bad idea, guys? Yes. The scaling issues for longer sentences. Exactly, right? We all have learned enough neural networks to know that our neural networks loves the weights to be in the range of -1 to 1. Okay. If the range of values goes beyond -1 to 1, there are exploding gradient problems, all kinds of problems creep in, right? So directly adding this is not a solution. What is one obvious way of solving this? An obvious way of solving this is what? Can I normalize this before adding? Okay, one hot encoding is acceptable. Okay, some people are saying no, some people are saying yes. Can somebody tell me why yes? Loses the order. Keep these between -1 to 1, loses the order. But uh, okay, so one moment. Let me explain what I mean by normalizing. Okay, let us say I have a sentence of length 20. Okay, let us say I have 0, 1, 2, 3 all the way up till 19. Okay, what if I simply add this divided by 20, this divided by 20, this divided by 20? Are these not probability values? Am I not adding them over here and getting this? So Arun, there's no question of losing the order here, right? There's no question of losing order here. And okay, it will not keep it in between -1 and 1, but it will be close by. See, Anil, we don't have to strictly stick to -1 and 1. We're okay with -3 to 3. We just don't want it to go too much beyond that, right? So this is also a valid strategy. But this also has a problem. Can anybody detect what the problem is? I'll give you a hint. You can have 20 length sentences, you can have 5 length sentences, you can have 3 length sentences. Varying words, bias towards last words, right? So now if I tell you the weight of my vector is 0.3, okay? This weightage changes if there are 3 words in the sentence. This weightage means something else if there are 5 words in the sentence. And this weightage means something else if there are 20 words in the sentence, right? Yes. So now there is no way for me to uniformly tell the neural network that 0.3 means it is in this part of the sentence, right? So Arun, just one word of caution. This is not an issue with higher weight in the last part of the sentence. This is okay. So in fact, we want that to happen, right? In this case, we're adding a bias to solve a problem. So that is not the issue here. The main reason why we don't do this is because now it's confusing to the neural network. For the same weight 0.3 that we're adding to this word to vec rate, if the sentence length was 3, this will mean something else. The sentence length was 5, it will mean something else. And if the sentence length was 20, it will mean something else, right? That's the issue here. So varying can be solved by padding. That is obviously a way to do it. You essentially pad all your sentences. But yeah, the issue with padding is, again, what I'm going to show you is all of these attention mechanisms, right? They're very they're very compute heavy. So padding is a very bad solution to this. As far as possible, we want to keep our input sentences very low here. So at a research level, we don't want to do padding because it will increase the time complexity of these unnecessarily. Because we have 120 length sentence and rest of them are 5 or 6, it makes no sense to pad everything to that. So that is the issue here. Okay. So now comes the problem of how should I input so that my network is able to understand my if I'm clear right now, please hit a yes if I'm still audible. Losing audio. Okay, breaking up. Yeah. Okay. Is it better now, guys? I detected that it's better now. I think it should be fine now. Yeah. Okay. Cool. So okay, after padding you lost. Let me re-explain the padding problem. Yeah. I stopped there myself, Arun. Actually, I stopped speaking because I saw that there was a network issue. So I'll just quickly recap what I said. I said that it's not good to pad because attention mechanisms are very time complex. Like time complexity of these is very bad. Okay. So that is the problem here. We don't want to pad. So now how do we fix this problem? Okay. So these guys came up with a very creative way. Okay. These guys, the transformers, the authors of this paper, attention is all you need. These guys came up with a very creative solution, which is what we're going to now go and study. So let us remember what are the constraints that we have. We have to make sure that whatever we are adding to our words, right, it has to not increase the range of values. So each entry that we see there, right, each entry that we see in our input to our neural network, okay, each the values over there should not go beyond -1 to 1, this range. So what are the two functions which have very nice properties like this? Do we know cosines and sine functions? Do we agree that these values never go beyond this thing? Indradeep, tan h is also valid. But to keep things simple, no, we'll simply use cosines because tan h is also built using cosines, right? Tan h is nothing but e to the power x plus e to the power minus x upon e to the power x minus e to the power minus x. So so using Euler's identity, you can express that as sine and cos ka linear combination. So the basic functions we use there is sine and cos. So we'll just use this. So now let us see how we're creating this positional encoding. Okay, the basic idea is this. Okay, let me tell you what the basic idea is. So let us say I have a word. This is a cat. Okay, what I'm going to do first is I'm going to apply word to vec over here. W2V. I'm going to apply this word to vec to all of these inputs. Okay. I want you guys to notice something over here. I'm allowing my inputs to be variable lengths to my network. Okay. We're going to build our architecture in a way that we are not dependent on the length of this, but we are not going to add any padding or anything. Okay. To deal with this, we're simply going to use this. So now what we can do is we can take this word to vec. Okay. These vectors are now going to come here. Let us assume that the word to vec dimensions are somewhere like in the range of 512. Let us assume that these are 512 length vectors. Okay. What we now have to do is create another set of vectors. Okay. So what I want to do now is I want to take this vector, add one more vector to this. Okay. So what I want to do here is I want to basically add all of these. Okay. The sum of these two are finally what I'm going to feed as the inputs to the rest of my network. Okay. The question is, how are we generating these vectors? And the answer to this is quite straightforward. What we're going to do to generate the first vector, okay, let us see. We're going to create these positional vectors using this formula, okay. I want you guys to notice something over here. First, let's look at the equation, then we will go to how this is visualized, right? So the positional encoding of the 0th index, okay? So you have pos over here, right? For the first one, for the word this over here, this is the pos over here is going to be 0, okay? I over here is going to be a variable. How are we making use of this I? Let us see, right? This I over here is actually telling me what is the entry in this vector that I'm generating here, okay? Which entry in this vector is getting controlled by this I? The position of this word is pos, okay? So are we clear on what pos and I are? Guys, quick confirmation. Are we clear on what pos means and what I means? Indradeep is not clear? Okay, let me repeat this. So there are two things, right? Okay, let me show you in this figure. This is 0, 1, 2, 3. This is pos. Okay. In this vector, now, if I say in this 5, so what is, first of all, to make this addition possible, this is also have to be 512 length vectors. Right? So the I equal to 0 is this one. I equal to 1 is this one, I equal to 2 is this one, and we have all of this up till I equal to 5 and 2, right? Yeah, yeah. So Indradeep and Arun, does this clarify things? Pos is the position of this word in the sentence. I is the index number for the corresponding vector over here, okay? So now this is how I'm going to do positional encoding. I'm going to convert this word into its word to vec. This is going to have 512. This positional encoding vector is also going to have length 512. How do I determine each entry over here? Each entry over there is going to be determined by this one, right? Each entry over there is going to be determined by this equation over here. The value at position 0 and index I, right? The value at position 0 and index I is going to be given by sine of 0 upon n to the power 2i by d. Okay. Yes. Yes, exactly, Arun. Row is I, then pos is column in the broad view. You're absolutely correct. So now I'm able to generate these vectors using this formula. So what I want you guys to notice is something here. For the even indices over here, I'm going to use sine. For the odd indices over here, I'm going to use cos. Okay. So the way I'm going to be generating these encoding vectors is as follows. I'm going to first take the position 0th word. I'm going to fix position to be 0 over here. Okay. Sine of 0 is going to be 0. Cos of 0 is going to be 1. Right. So for the position 0 word, can you guys imagine that? Okay. Can you guys imagine that this is going to be 0, 1, 0, 1, 0, 1. up till 512. I want you guys to first focus here, guys. I will explain all your questions. First focus here. If I set pos to 0, if I set n to some very large value, 2i over here is telling me that I'm dealing with the even numbered indices in this positional encoding vector. Okay. D over here is the dimension of this vector. So over here, D is this value. 512 is what D is. Okay. Yes. So Indradeep and Arun, you're absolutely correct. D over here is 512. So to generate this positional encoding vector, what I'm going to do is I'm going to apply pos equal to 0. I'm going to take I all the way from 0 to 256. Are you guys convinced that if I goes from 0 to 256, 2i will go to 0 to 512 and 2i plus 1 will also go from 1 to 512, 511 actually? So now what I'm going to do is for this index, so for the even indexes, I'm going to apply a sign on the pos upon n to the power 2i by d. Okay. On the odd indices, I'm going to apply a cos function on pos upon n to the power 2i by d. Okay. This is what this looks like. So essentially now what I have is when my position is 0, this is by default going to be 0, right? So all the even length, all the even entries in my vector are now going to be zeros. All the odd ones are going to be ones because cos of 0 is 1. So my first vector, right? So pos 0 is going to be added to something which looks like this 0, 1, 0, 1, 0, 1 alternating till 512. Okay. How do we visualize the same idea? For position 0, look at this. The green points over here are telling me from which part of this cosine I'm taking it, right? So what I want you guys to understand here is n to the power 2i by d, right? N to the power 2i by d is acting like the frequency of this cosine. So for 2i equal to 0, this is nothing but 1, right? So this will be the cosine or the sine with the highest frequency. When my 2i by d goes higher, notice that this one has a lower frequency than this one, correct? In the time it took for this guy to complete 2 cycles, this guy has completed only 1 cycle over here. Do you guys see this? Guys? Do you guys see this? The frequency of this sinusoid is basically half of the frequency of this one. Okay. So that is what this n to the power 2i by d is doing. Okay. So for the first two positions, so for pos equal to 0 and for I equal to this, right? For I equal to 0 and 1, this is the sinusoid from where I'm taking these values. For the positions 2 and 3, this is the sinusoid from where I'm taking the values. And as I keep progressing, what's going to happen is the next two are going to be a slower sinusoid. After that, slower sinusoids. So this is how I'm essentially making my position vectors, right? So pos 0 will have these green points. Pos 1 will have all of these red points over here. Pos 2 will have all of these purple points. Pos 3 will have all of these blue points. Okay. So that is essentially how this formula is generating these positional encoded vectors. Okay. That is how these formulae are generating these positional encoded vectors. So once I apply this formula, I'm able to get positional encodings for all of the vectors in my sentence. Is this part clear to everyone? How I'm generating my positional encodings? I'm getting these positional encodings by using cosine and sines. The advantages of doing this is that all the entries, right? All the entries in these vectors are going to be between 0 and 1. So I'm not changing the weights of any of these by a large margin, right? That is how we are able to generate these values. Okay, cool. So Arun, I will repeat once for you in short. In short, it's as follows, okay? Let us say, so first of all, what are my parameters? I have 3 parameters over here. First is D, then I have pos, then I have this, right? I. So these are the 3 things that I need to understand. Let us see how each of these is understanding. What pos will control is where am I taking the sample of this from? Okay. So pos is basically controlling, am I taking it from this or am I taking it from this or this? So pos is controlling that part. What this I is controlling is what is the frequency of the sinusoid from where my values are coming, right? So for low I's, we have the most frequency sinusoids. As I keeps increasing, uh, we will take less and less frequency sinusoids. Okay. And finally, D over here is controlling how many of these I will have, right? So I will basically go from 0 to D minus 1, right? So because I is going from 0 to D minus 1, D will control how many of these I need to make my positions. So once I put all of these three together, I get these positional encodings over here. Is it now clear, Arun? So it acts like a sigmoid gate to highlight which words to focus. Yes, Arun. It acts like a sigmoid gate to highlight which part to focus. But unlike a sigmoid gate, right? Okay. Unlike a sigmoid gate, right? This is generating vectors. Sigmoids will just apply to one value, right? So the difference between a sigmoid and these vectors is this is a way for me to generate vectors which are of the same length as my word to vex. Okay. That's the difference. That's the difference here. Okay. Cool. So now that we have understood how my positional vector is working, let us go and understand the rest of these things. Okay, cool. So now that I'm done with my positional encoding, what I want you to see here is the output of this positional encoding is coming and sitting on is an input to this layer called multi-headed attention. Okay, and if you observe carefully, there is a pathway which is going from this to this, right? There is a pathway which is going from this to this. What is this kind of a pathway called? If we take this and simply pass it ahead, it's a skip connection. Exactly. You're absolutely right. This is a skip connection. So in our transformer, our first step is to do positional encoding. Then we will essentially pass it to a multi-headed attention mechanism. Okay. And we're also going to give it the freedom of doing the skip connection, right? This is what we're doing. So now let us understand what this multi-headed attention is exactly. Okay. Let us focus on this part now. Okay. So my multi-headed attention component looks like this. Okay. My multi-headed attention component looks like this. So this is my positional encoding. This is the concept of self-attention. This is self-attention again, right? Okay. So now comes the question of what is multi-headed self-attention. Okay. So what we have to understand here is this is a multi-headed self-attention mechanism. So let's take an example to understand this. Right? Okay. So first, let us quickly recall what was single-headed self-attention, right? So the components of a single-headed self-attention were key, value, right? Key and value. So let us say I have the sentence, this is a cat, okay? Let us say the word to vec encodings of these are 512 length vectors, right? The word to vec encodings of these are 512, and this is basically 0 to 4, 0 to 3, right? 0, 1, 2, 3. So I essentially have n equal to 4 words in the sentence. Okay. If I had to build a key matrix over here, when I'm building my key matrix, remember that I have to put the words on the rows, okay? And I have to put the, I have to put the word to vec on the rows, and I have to stack. Yeah, so each row over here is now going to be a word to vec, and the number of words that I'm doing this for will be stacked as the rows over here. So can you guys quickly tell me what is the dimension of this matrix? How many rows will I have? How many columns? Won't it be the opposite? I will have 4 cross 512, right? 4 cross 512. Indradeep. Each row over here is a word to vec. So the row dimension over here is 512. This is 4. Yeah. So vocab is V. Perfect. Uh, Arun, vocab is V. Arun, when we were applying when we were applying attention, right? Did we take the vocab or did we take one sentence at a time? Arun? It's words in a sentence, right? Attention mechanisms do it for a sentence. They don't do it for this. So since we're dealing with words in a sentence, my this matrix is going to look like this, 4 cross 5 12. Okay. My value in self-attention, what is the relationship between key and value? Same, right? So this is also going to be 4 cross 5 12. Okay. Where my rows are this, right? In self-attention, what is key, value, and query? In self-attention, what is query, guys? Is it the same as key and value? Okay, it's the same as key and value, right? So essentially now, my query is also going to look like this, 4 cross 5 12. Okay, my query is also going to look like this. So let us quickly recollect how we did self-attention, right? We basically took the key matrix, we took the query matrix, and we did a dot product between them, right? Okay. So typically what we do is we do key into query transpose. The way I have written it here, I'll have to do key into query transpose. This will give me what dimensions as my vector over here? If I do key into query transpose, what will be the dimensions of this matrix? 4 cross 4, right? 4 cross 4. So what is nice now is that I have this 4 cross 4 matrix which is giving me the relationship between this sentence and the words in the same sentence, right? This is going to calculate the similarity between these two. Okay. And if you remember, in transformer networks, we don't do dot product, we do scale dot product. So I have to scale this somehow, right? So what do I have to put over here? What will be the number that comes over here, guys? The number. I don't want the dimension. What is the dimension here? Isn't the dimension 512? No, 512, right? Dimension of word to vec. It will be 512. So I will have to put under root of 512 in the denominator. Whatever this gives me will be the similarity score. Okay, similarity score. If I now take the similarity score, pass it through softmax, I will get my self-attention. I'll get my attention weights, right? And then the attention weights is what I can apply back to the value matrix, which is nothing but my key matrix, right? So in my self-attention now, these are the steps which are going to be followed. Okay, let's now figure out how this attention module is working over here. Okay, in our diagram over here. So think of it this way. I have some inputs which are coming here. The input is a sentence. I have done the input embedding. I have done the positional embedding. I'm now going to do something which is known as a self-attention on this. But the difference here is I'm not happy with self-attention. I want a multi-headed attention over here, right? So in a multi-headed attention, what I'm going to do is I'm going to have to change strategies over here. Okay, I'm going to have a change strategies over here. So let us now highlight the difference between single head self-attention and multi-head self-attention. Okay, let's figure this out. All right, okay. So in my single-headed self-attention, my key matrix was formed by putting word to vec as the rows. Rows are word to vec vectors. Okay, this is single and I'll put multi over here. Can you guys tell me if the rows are word to vec vectors and I fix the word to vec weights, is any part of this trainable? Is any part of this trainable? No, right? It's not trainable right now. So in multi-headed attention, since I'm using a neural network sitting there, what I will have to do is I will have to add a trainable component, right? So the main difference between single and multi is now my key is going to be done this way. Okay. I'm going to get my key matrix by first pass word to vec outputs through a dense layer. Then the outputs of the dense layer is the key matrix. Okay. So now in this multi-headed attention component, I want to put some trainable component, right? How am I doing that? I'm simply going to take my word2vec vectors. I'm going to pass it through a dense layer. The output of that dense layer is what is going to generate my key over here. Okay. If you want to visualize this, right? I have this way to visualize this. Let me quickly show you. Wait, I think it's in this. Let's quickly go up the visualization for this. Yeah, no, this is what self-attention looks like. Um, yeah, this is it, right? So this is the example for the same concept case. I have these two words here called thinking machines. These are the word-to-vec representations of this. Note that I have n equal to 2 over here, right? So my thinking occupies the first row, my machines occupies the second row. This gives me my X matrix. What I'm now going to do is I'm going to take this X matrix, I'm going to pass it through this dense layer matrix here. Note that there are no bias terms over here, okay? So I'm simply going to do a matrix multiplication between this X and this W0Q to get this Q0, okay? I'm going to take this X, I'm going to multiply it with this W0K to get this K0. I'm going to take this and multiply it with W0V to get this V0, okay? And now I'm going to use this Q0, K0, V0 as my query key and values, right? So understand now that because I'm doing things this way, my query key and value need not have to be the same thing. I have different matrices over here, which are giving me different Q, K, and V values over here, right? Is this part clear to everyone? Guys? I'm essentially now taking my input. I'm using a dense layer to do things. So I'm getting this Q0, K0, V0 by applying this through a dense layer. Indradeep, yes, we learn these matrices through backpropagation. You're absolutely correct. Once I have these Q0, K0, V0 values, what I'm going to do is I'm going to take an inner product now. So I'm going to do K0 transpose Q0, right? Whatever, like I'm going to figure out what the dimensions are. We'll have to keep track of the dimensions. Remember that the output has to be 4 cross 1, right? It has to be n cross 1. Why n cross 1? Because we're going to scale each of these things with these attention weights, right? So we have to perform these matrix operations in a way that the final attention weight is going to be 4 cross 1. Okay. So once we have that, we will multiply those attention weights with this V0 matrix to get this Z0 matrix. So this is going to be the output of the first self-attention head. Okay, cool. I can now do the same thing, right? Can you guys imagine that if I was using one dense layer here to get my Q0, K0, V0 vectors here, can I not simply repeat this n times to add multiple heads, right? So the multi-head part comes from this. I'm first taking these, the first dense layers are going to give me my first set of attention outputs. Another one will give me another set of attention outputs. So I'm going to take all of these and I'm going to gather them into the single matrix called Z. And finally, I'm going to apply one dense layer on this output Z to give the final output of this multi-headed attention component. Okay. The final output of this multi-headed attention component is going to be the output of this through each of these linear layers. Okay. Are we now clear on how this multi-headed attention component is computed? Guys? Okay. So some people understood it. If you did not understand or did not follow this, guys, We can discuss a quick implementation next class. So I will be attaching this notebook over here, right? Guys, this is a detailed notebook which implements every part of a new transformer over here. Okay. So neural machine translation with a transformer in Keras. I'll just share this link with you guys. Let me just share this link with you. This is essentially a from scratch implementation of this. So we'll be studying this next class maybe. But if you have any doubts as to how this is done, you can simply go to this notebook and see this part. Okay. I'll show you where this multi-headed attention is implemented. So this is the positional encoding part. This is the code for that. The multi-head attention part is over here, right? Yeah. So you can come to this part of the notebook, the base attention layer. You can come to this part and see how this is implemented if you're interested. Okay, cool. Let me address Arun's question. So these W0, K0, and Q0 act like the filters in comparison to the CNN. Are they filters? Okay, no, Arun, that would be wrong. I would suggest one. Yeah, it won't be like that. Arun, you remember mobile net? You remember mobile net, Arun? You remember how we took three? We did not know which convolution was best, right? Sorry, not mobile net. I'm so sorry. Do you remember inception net? In inception net, the basic problem was that we did not know which convolution dimensions is the best, right? 3 cross 3 was there, 5 cross 5 was there, 7 cross 7 was there. So what we did was we parallelly did all of them and then we passed it ahead, right? So this is the same idea. I don't know which attention will work best. So what I will do is I will create 8 of them and let all 8 of them learn where to pay attention. Okay. Indradeep is a bit confused with the shapes of the last matrices in the diagram. Okay, let's go through this concretely. I will show you this, right? So let us do this. Let us calculate the shape of these matrices from here. Okay. I'll take this over here. I'll take this image over here and let us use this. Let us imagine what the shapes are. Okay. So over here, if you notice, my n is equal to 2. My d dimension of the word-to-vec embedding is 4, right? Over here, if you notice, W naught is a 3 cross 4, a 4 cross 3 matrix, right? 4 cross 3 matrix, okay? This is a 2 cross 4 matrix, right? So when I take this input and I pass it through this linear layer, what this is going to do is it's essentially going to take this dimension 4 and make it dimension 3, right? So once I pass this input through these layers, the outputs that I'm going to get for Q0 and K0 and V0 is going to be 2 cross 3, right? Indradeep, are you following so far? It is going to be 2 cross 3. So once I have this 2 cross 3, what I'm going to do is my attention weights is going to be softmax of, okay, what is it going to be now? I need 2 cross 3 as the thing, right? I need a two-dimensional thing here. So to make it two-dimensional, what I'll have to do is I'll have to take Q0, I'll have to multiply it with what? K0. Do I have to take a transpose here? No, I don't have to take a transpose here. I have to do Q0, K0 transpose by under root of D, which is 4, right? This is what I have to do, Indradeep. So now my attention weight, since this is a softmax, right, Indradeep, this softmax will be essentially applied to the output of this, right? The output of this is going to be 2 cross 2. Softmax is going to be applied row wise, not column wise, right? Softmax is now going to be applied row wise. So then when I apply softmax row wise, this is going to give me a 2 cross 1 vector, right? So now what I'm going to do is I'm going to take this 2 cross 1 vector and I'm going to multiply the first entry. So think of this as A comma B, okay? I'm going to take A, I'm going to multiply it with this row. I'm going to take B and I'm going to multiply it with this row. This is how I'm going to get my Z0. Sorry, my bad. I'm so sorry. I'm going to take this A and multiply it with V0. I'm going to take this B, multiply it with V0 second row, and then I'm going to get this Z0 matrix. So that is how we get this. Is this now clear? Huh. So once I have this Z0 now, this Z0 is now nothing but my context vector. This is my context vector, right? Now let us assume that I made how many? Let us assume that I put two such context vectors, right? This is multi-headed attention. So I'm going to have one set of outputs from this, one set of outputs from this. So then what I'm going to do is I'm going to take this and I'm going to stack them together. Okay. This is actually drawn wrong. What I'm going to do is I'm going to put Z0 here, Z1 here, right? So think of this resultant thing as 4 cross 3, right? Think of this as a 4 cross 3 matrix. Once I have this 4 cross 3 matrix, I'm going to apply a W0 on this. This is the final dense layer. This is going to operate on all the attention head outputs combined. And then the output of this layer is what is going to be the output of this overall multi-headed attention layer. Okay. The output of this overall multi-headed attention layer is going to be this. Are we now clear on how this is working? Multi-headed attention? Indradeep? Okay, awesome. Cool. So now let us see what to do with this next. Okay, let's see what to do with this next. Now what I'm going to do is the output of this multi-headed attention, right? I'm going to take, so guys, think of it this way. The multi-headed attention layer is going to give me one Z, right? Let us imagine for now that the Z output is 2 cross 3, right? Do you notice that the Z's dimension and my input dimension are related? Do you notice that these two are related? Z0 and input dimensions. This was 2 cross 4, this is 2 cross 3. Can I do something so that this is also the same dimension as this? Can I do something here? Where did I go wrong in this sequence? I went wrong in choosing this matrices, right? Yeah. So if I now, instead of doing 4 cross 3, if I had done 4 cross 4 here, right? Instead of 4 cross 3, if I had done 4 cross 4, Z0's dimension and X's dimension will have to be the same, right? Yeah, multiply to get correct dimension, exactly. So while I'm implementing my multi-headed self-attention, I have to take care that the input dimension and this dimension is the same. Why is this important? Because of this skip connection over here. Can I add matrices if they are of different dimensions? No, right? I cannot. So what I have to do now is I have to make sure that key query value, whatever outputs I'm getting from this, that has to be the same dimension over here. Okay. If it is of the same dimension, then I can do this add and norm. Okay. So let me explain what this add and norm layer means. Okay. So this is my multi-headed attention output. This is coming from the skip connection. This is basically X, right? Which is the input which I give. So the add and normalize is going to basically take the sum of these two to give me the final one over here. Okay. This is going to be a 2 cross 3, which is giving me a final layer over here. Okay. This output I'm going to normalize using the whole thing. Okay. Normalize. So what I'm going to do is I'm going to take the, so this is where I'm going to apply layer normalization. So let me just show you how the layer normalization layer works. Okay. So layer normalization. So layer normalization is exactly like batch normalization. The main difference being is that batch normalization will basically do it for an entire batch, right? The thing about layer normalization is it will do it individually for each feature maps over here. Okay. So exactly like how batch normalization was calculating the mean and sigma and then basically dividing each entry by sigma and subtracting the mean from it, right? That step is going to be repeated here. Only thing is, if this was a batch size of 32, like let us say this was 32, right? It would do this once for all the 32 layers individually. Okay. So in batch norm, we take the whole thing and operate on it. In layer normalization, what we do is we will just take the first output. Okay. The first multi-headed attention output, we will apply normalization on that with just these values. Then we'll take the next one, apply the same thing and so on. So that is the meaning of this this component. Okay, that is the meaning of this component. So I have this multi-headed attention. I have this skip connection coming over here. The output of this multi-headed attention is going to go to this add and norm layer. What's happening in this add and norm layer is that these two are getting added with each other, and then the resulting addition, right? This is going to get normalized. How is it going to get normalized? One feature map at a time. Okay. So this is how we get the output of this transformer. Once I do this, I can simply pass these outputs through a feed forward network over here, right? What is a feed forward network, guys? Is it not just a collection of dense and dense and activations? So think of this as a collection of dense and activation layers. Once I do this, I will again have an add and norm layer, and this whole thing now, this whole thing. So let me now tell you what this is. So 1 minute, I'll actually get the figure from this. Where did that go? Just give me 1 second, guys. I'll quickly, this one. So this whole thing now, this whole thing is now known as a encoder block. Okay. So what all comes in the encoder block? Let us quickly see. You take your word to vex, you do positional encoding, you pass it through the self-attention mechanism, which I just showed you what it was. You'll get this Z1 and Z2, right? This is Z1 and Z2. This is multi-headed self-attention. So remember that there's going to be some depth over here. This you're going to now pass to this add and normalize, where you're simply going to add these two, normalize it. The output of this is going to be passed to the feed forward network. We're again going to do an add and normalize, where we have a skip connection from here to here. Okay. And the final outputs of this is what we're going to call the output of encoder block 1. Okay. In the original paper, right, this is exactly what they're doing. This is known as one encoder block. Notice that we have this n into this, right? So for the results in this paper, they selected an n of 6. So what I want you guys to imagine is, now whatever we have discussed for the encoder block, imagine 6 of these, and then the output of the 6th one will go and come over here to this decoder block. Okay. So guys, it's it's 11:22. It really won't be possible for me to cover this decoder architecture today. What I'm going to do is, next time what we're going to do is, we're going to resume from this point. Okay, we're going to discuss how the decoder architecture works. We're going to see how each of these things are implemented, and we're going to carry forward our discussion to BERT. Okay, so I would like to end the class here. I really apologize for taking 20 minutes extra. I would like to kind of stop here. What I want you guys to just remember for next class is, we had stopped here, right? Where we have this, we have basically discussed in detail what this encoder block looks like. Okay. What we're going to see now is, how is this encoder block interacting with the decoder block to basically get my final output. So let me just do a quick look ahead over here, right? If you notice, there is this very mysterious looking multi-headed attention coming over here, right? It's called something else in the paper. So this is known as multi-head attention, but this is also something else. So this is a multi-head attention where the outputs of this are giving me two of the things. So this is giving me keys and values. Sorry, this is giving me keys and queries. This is going to give me my value. Okay, this part of my decoder is going to give my value for this multi-headed attention block. And then this whole decoder block is constructed as follows, right? So what we're going to do next time is, we're going to study what masked multi-headed attention is. We're going to study what multi-headed attention is. We're going to see how to construct the rest of this, and we're going to apply this problem for neural machine translation. Okay. So we're going to discuss this next class. So what I would request you guys to do is, any doubts that you may have, please ask them now. First, I would like to address, if possible, Anindya's doubt. Okay. So Anindya, if you're still around, please unmute yourself. I want to address that question that you raised, because this is kind of important, right? Okay. So please go ahead, Anindya.
Can you hear
Yeah,
me?
yeah. I'm perfectly audible. I'm able to hear you now. Yeah. Okay.
So I think better would be we go for a one-on-one call.
Okay.
let's, for the interest of time, let's go ahead with the other queries.
Okay.
So probably that will be one-to-one feedback for you and me, and then we will get it together in a separate
Okay.
call.
So
Is
Anindya,
that fine?
it turns out that there are no other questions right now in the questions tab. I see no other questions.
Okay.
Yours is the only one.
Okay.
Yeah.
Okay.
Okay.
If you would like to go ahead, then no problem. So
Um,
my
yeah. Okay. Sure.
yeah, let's go
Yeah.
ahead. So basically, what I was trying to emphasize on is see, you said that certain things there are you said your point that there are a lot of things about oops and all you said, and then linear algebra you
Hmm.
said. I totally agree on those
Hmm.
parts. But the point is, you said that something that we were not properly going through, and that's why we are lagging on some
Yeah.
aspect.
Yeah.
Okay, it's partially true, but that is based on certain
Okay.
assumptions.
Yeah.
Okay, first assumption is you are assuming that, for example, this is a batch of same
Hmm.
class with same power of reception,
Yeah.
right?
Yeah.
Okay, when Scalar
Hmm.
started with the batch of beginners, intermediate, and
Hmm.
advanced, right?
Yes.
Now you will agree on that part that over this
Hmm.
batch, some of the people, they are already, some of the students, they have the background on all this NLP and CNN, right?
Yes.
So they come up with preset mindset and some pre-learning,
Hmm.
right?
Yes.
Right.
Yes.
So in that sense, it's not the same learning level that we are all in,
Yeah. Hmm.
right?
Hmm.
Okay. So if some people are already with the preset, then they might be at level 1 and level 2, level 3.
Okay.
So from that aspect, the assumption from Scalar is they are considering everyone on the same level.
Yeah.
First thing, that is not
Okay.
correct. Second thing is other aspect is, my intent was that if everyone is going through, why not Scalar is actually going through, continuing with all the batch of beginner, intermediate, and advanced,
Hmm. Yeah.
right? I understand there are certain constraints in terms of logistics constraint that you don't have so many people in the last batch, whether 20, 24 people are on the batch,
Correct.
and you cannot run all those
Hmm.
things. I totally understand that.
Yes. Yes.
Now coming back to the topic
Hmm.
that we are trying to see that the research paper.
Hmm.
See, the intent of this NLP is very important because with the everything is going toward that direction,
Yeah.
right? My only intention is not to, I saw that you're a bit upset, but
Like,
my
yeah.
intention was not to keep you
It's
upset.
okay, Anindya.
My
Don't worry about that. See, like, I'm also human.
yeah
I also have some emotions, but
yeah
I want to address this because,
yeah
like, the reason why I want to
yeah
address this with you is because
yeah
I
address.
understand this. Because, see, I have also been on the other side, okay, Anindya? I have,
Yeah.
yeah,
So
yeah,
it is nothing, no personal feedback we are going. We are trying to make the system
okay,
improved, right?
yes, yes,
So that's the only intent. I'm just carry forwarding all this
correct,
feedback.
correct,
My only thing is, see, you cannot think all your child in the same level,
yeah,
right? That's the point.
yeah,
You cannot think that if somebody is not understanding, they exam simple
yeah,
examples. See, people has to go through 4 and 5 round of recording,
yeah,
but your assumption is people are in a they are not doing things correctly. I would like to correct you on that part,
yeah,
because
yeah,
people are
yeah, yeah,
putting,
yeah.
at least I cannot take the guarantee of other people,
Hmm.
but at least from my aspect, I am going through all those
Yes,
things. Okay,
yes,
now think it is the other way
yes,
around. So if we are understanding things in a layman
hmm.
way, then we might not need to go through that round of
Yeah,
iterations.
yeah,
Yeah, there might be scale of like people might not understand everything in a single
hmm.
class, but one class, if they go through another round of recording, they will be able to
Hmm.
understand. Now you see that
Yeah,
difference. It's not like you will see that you can take a poll.
hmm.
It's not my opinion, you should be biased with my opinion,
Yeah,
right?
yeah,
You can take a poll in the class and you can find out how, because all these are new
hmm.
topics. You said the linear algebra and oops and all these things.
Hmm.
See, I totally agree on that
Hmm.
part, but these are, even you will also agree, when you are
Yeah,
teaching, certain things are also getting confused, right?
yeah,
We are all getting, because this is something, these are very difficult
yeah,
topics, and we'll not be able to get through it at first
yeah,
level. So you have to think us about us from that
hmm.
aspect, right? If you are done with one class and come in the second class with, I don't know, 80% or 90% of retention,
Hmm.
that is not a right assumption you should be believing with. and scalar should not be at that level.
Okay.
Okay. So that's the only thing I just want to convey you. So this is something where these are difficult topic. We should come again and give it like the way you always do,
Yeah.
right? You always come up with a revision
Yeah.
and all. But what I'm trying to say is give it some more time, like one class for BERT, one class for transformer. Can't we extend it for 2 class, 3 class, like that? Because these are very important topics. And going forward, rather than traditional ML algorithms, which are the base, these are going to take it to the other level where we are looking for the jobs, right? So these are very important topics. Why we are trying to just giving a limit of like 1 month, so many classes we have to do, right? So these are very important. Scalar has to understand that, because the retention of, because we at the end we are all professionals. Some people are from the academic background. They're coming and they don't attend the class after the work, right? So we have to see that people are coming and they are even putting 3 to 4 hours repetition of classes. What is lagging? Is it only the student lagging? Is it something that we can also improve?
Yes.
This is nothing against. So that you have to start thinking on those lines. That's the only feedback I have.
I totally agree. Okay. So, Anindya, so I'm going to give you one response. I request you to stay back and hear my responses. There
Yeah.
are some things which we can do on our side to improve things. There are some things which you can do on your side to improve things. So I just want to
Correct.
address
Exactly.
both of them, right? I totally
Exactly.
understand this. See, Anindya, the reason why I'm staying back, why I'm patiently addressing this in public, right, with your batchmates, why I wanted to do this is because I have been in your position hundreds of times in my life. Okay, I have never been the brightest
Yeah.
student. I have never been the fastest student. I have also struggled with people who have gone way ahead of me, and I had to multiple times catch up to them. I'll give you a very simple example. In IISc, there are these undergraduate students who, for the first 2 to 3 years, are just taught core mathematics at the toughest level. Okay, then these guys
Right.
come into our graduate level courses. They score the top marks, and all the PhD and master students are left thinking, what has gone wrong with our education that these people are coming at?
Exactly.
Yeah, so that is what.
Exactly.
So I have been there, Anindya, and I feel for you.
Yeah.
That is one reason why I
Yeah.
want to stay back and address this, right? See, I will tell you my personal point of view, then I will come from Scalar's point of view. Okay. So from my personal point of view, I'll tell you how I dealt with that situation. First, I'll tell you my strategies. I'm not saying ki you should do this, and I'm not expecting you also to do this, because studying in a university and working to support your family while updating yourself are two very different things. Okay. But I just want to share my experience so that I'm justified from my point of view, right? See, I'm also a human being. I also want to make sure everyone is happy. From that point of view, I just want to give you one answer. Just let me tell you how I dealt with that. This issue of batch homogeneity. In IISc, the major issue is this, okay? Uh, Courses are taught at a very mathematical level. You ask anybody from IISc, they will say that if you don't know maths, you cannot survive in IISc. Okay. When I went as a computer science engineer, I did not know anything about discrete math. I did not know calculus. I was struggling with differentiation integration back in my first, second years. Okay. This is my honest statement to you. The UG students came, they scored the top marks. I was giving in 110%. Okay. And those guys were giving 1/10 of the effort I was putting. It still looked like, I was lagging behind. Okay. And I was very frustrated. I went to my professor and I asked him, boss, what do I do? I don't think I'm fit for a PhD. I'll tell you what my professor told me. And that is what inspired me a little bit to fight. So I just want to tell you this because I want you to believe one thing. Okay. All human beings are born with the same capabilities. Our circumstances make our capabilities different at different points. But if your destination is clear, right, this is one hurdle you will have to overcome. This is what my professor told me. You want your PhD, don't make this weak excuse that other people are more competent than me, so I cannot do. The idea behind doing a PhD, the idea behind doing research work, the idea behind forming teams to solve problems. Why don't people just have one person companies, right? Why is it that so many people have to come together to solve problems? It's because nobody has the capacity to solve the problem in its entirety. Okay. So my professor's advice to me was this. The problem with me at that time, my thinking was, I was thinking still in 10th and 12th and college terms that, okay, there is one exam which all of us will write, and that exam numbers will distinguish, tell me how good I'm doing, right? That was the basic problem. The School, college level, everyone starts at the same starting line. But at a PhD, not everyone starts at the same starting line. My starting line was way behind than these people whom I was angry with. Okay. What my professor told me was the finish line is the same for everyone and it's a marathon. It's not a sprint. If you treat it like a marathon, if you try to rest less than the other people, someday you will catch up to them. And if you're able to catch up to them on that day, you will be even more encouraged to surpass them, right? So my professor told me, see, you're here for a PhD for 5 years. Okay. Anindya, tell me one thing. Do we have any limit on our lives? Can we say that there is a limit on our lives?
See,
Hmm.
I
No,
understand
no, no, no.
the
1 minute. Yeah.
direction you are
Yeah.
going in. See, we are not here giving any
Yeah.
excuse. See, you have to think from our perspective.
Yes.
See, I'm not giving an excuse that we cannot do
Yeah.
it. We can definitely
Yeah.
do it. There is no doubt about
Yes.
it. But the problem is what I'm saying is
Hmm.
you are giving us the direction where we can do.
Yeah.
Scalar is only communicating in our direction. Scalar is not negotiating in terms of what they can do.
Got it.
You have given us 2 points, right? So that has to improve. See,
Yeah,
otherwise you will
hold on, Anitya. You're
yeah,
not finished listening to me. I was just addressing
yeah,
issue one. I have not yet come here. Okay. I have
yeah.
not yet
Okay,
talked about these two. I'm not trying to give you a direction where आप ये कर लो, मैं अपना देखूंगा. That is not what I'm doing here. Okay. I'm trying to tell you,
okay,
I'm trying to build a solution used by addressing each of these points. So hear me out. Okay. Don't
okay,
assume
sure,
what I'm
sure.
going to say. Okay. Don't assume.
Okay,
Hear me out. First of all, this issue of homogeneity, let me tell you, practically speaking, it's not possible for everybody to start at the same starting point. Okay. We have to deal with this sometimes in our life that some people are ahead, some people are behind, and we have to make sure that our destination is the same and we have to keep racing. So, this is one point of view I'm telling you. I have not yet talked about what we're going to end up doing. So, hold on. Now, let's talk about this. Okay. Let us say that you are at different starting points. Okay. Now, let us come to this second point. Let me address this one now. Okay. Second
mhm,
point is more classes for more important topics. So, let us now make this assumption. We have beginner, we have intermediate, we have advanced guys. Okay. The starting line is different for all of them. The destination is still here, right? So your argument is that basically we should have a different course for this, different course for this, and different course of this. I'm 100% in agreement with you. I'm 100% in agreement with, okay, different people have different needs, so they should have different scripts. From a personal point of view, what I've tried to do from my end at least is from the start, I have tried to be very communicative. Okay. I'm aware of this problem. I'm aware that the batch is not proper. So from the beginning, I have been telling guys, stop me if you don't understand. Stop me if you don't understand. Tell me if there's an issue happening. If you're not able to get something, I will repeat 100 times. I made that commitment, right? Why am I listening to this 2 classes before this module ends? Can you just tell me one thing? Why am I listening to this today? I thought everything. So till today, till you raised this point in class, I was under the impression that I have successfully managed to teach a mixed batch. Today, I'm getting the feedback that no, whatever way I have been doing, I have only been listening to these people and not to these people. Okay, because I was sent into this batch with this feedback that this is a mixed batch, you have to handle it carefully. Okay, so from the start, I've tried my best to do this. Okay, if you're already aware you're here, I have from the beginning of the CV module given you the power to slow me down, right? You remember I keep saying slow me down, stop me, ask me. That's possible, right? I've not seen that happen. I've seen people lose hope. I've seen people say, "Oh, ये हमसे नहीं हो पाएगा."
because
Yeah.
see, there are two reasons
Hmm.
of
Hmm.
doing it.
Hmm.
See, honestly speaking, so there are certain ways. Don't take it
I won't. I
personal,
won't. I won't. I
Dhruv.
won't. I won't. Yeah.
Yeah. So I was going through the CNN module,
Hmm.
your sessions and Srikanth sir
Yeah.
sessions.
Yeah.
Okay, because I when I was going through your
Hmm.
sessions, it was taking a lot of time to grasp because teaching is a different
Hmm.
style where you have to you will not be able to master it within a single
Correct.
day.
Yes.
Okay, so it's our own. Maybe not we are not perfect at everything. We might go there in some
Hmm.
day. So there are certain ways you you will find and understand based on teaching styles.
Yeah. Okay.
Okay, so that's how I have coped up because whenever I'm going through each of your module,
Hmm.
I'm not bothering the flow of the class
Hmm.
because I don't want to bother the flow of the
Hmm.
class. I am at the back end. I had to go through the previous recording and going
Hmm.
through it. So this is my way of
Got
doing
it.
it. Okay. So this is my explanation how I'm going
Got
through
it.
it, and I'm getting more grip to it.
Okay. Perfect.
I'm getting more confidence to it. So now similarly, some people see losing understanding the grip in the class. There are two ways of it. Either the it's not interesting, or either the it is being portrayed is not making it interesting.
Okay.
So other than you are doing your bit,
Yeah.
but you have to always introspect yourself and understand why it is going wrong.
Okay.
Because the feedback system,
Hmm.
if the feedback system is, I believe people have gone, because I have talked to many people as well. They are also giving feedback, but feedback is not being considered where they are going wrong.
Okay.
So those things, can you answer me that question? Are you getting any feedback on the lectures that you are getting
Yeah.
for all the
Yeah.
classes?
There are
So
people who go to raise support tickets. I get feedback through that route. There are people who say that the way I'm teaching is a little complicated. I have worked on those things. There were 3 points where I was asked to stop teaching, take a break, and figure out how to teach this mixed match. There were 3 points where Scalar told me to improve the way I was teaching or stop teaching. Okay.
yeah,
Yeah.
so you getting the point,
Yes, I
right?
am.
So these are, see, it's not like black and white, there are gray
Yeah, of
areas.
course.
So it's not it's, so we cannot see that it's wrong from the student side why they have not raised the question. See, sometimes you will say, okay, do this, and do that. At some point, if you see that the people is not the people who are listening to you is not making interesting, so then you'll stop raising thing, right? So this is another way of looking at it. So it's not like I'm saying it's your fault or it's our fault. It's both fault.
Okay.
I totally agree with that. It's both fault, but there are certain things could have been done improved rather than continuing with that way.
Okay.
That's what I was trying to make a point now.
Yeah, makes sense. So what are your concrete suggestions? Clearly, I have not
My concrete
understood from your
my
feedback.
my
Give me your
my,
feedback.
my
Yeah.
suggestion my feedback is, see, scalar should have been doing, because complex topics, people see, you initially said in your first statement that when you are taking, you have much more grip on the CNN
Yeah.
part. You have not worked on the NLP
Yeah.
part,
Yeah.
right? I'm not saying the underestimating your capabilities and all, but at the same time, Scalar already understand, and after getting all this feedback, they should have given it with the training and sort of thing, like as somebody who are into that domain. So don't take it personal way.
Yeah.
Somebody into that domain and say how to make it more interesting, where it's taking things are going wrong, but nothing is coming from that part. So that is more frustrating for us.
Got it. Can you tell me one thing? Did you notice a difference in the details or the technical part on the CV or NLP
There
side?
is a difference. There is a difference.
Okay.
I truly agree. You are working on it. There is a difference, but still, it's not to the level that I mean we were actually expecting. At least I was expecting.
Okay.
So I would say, like, my honest suggestion is, I would say that you can talk to Verma sir, because like the way, it's my personal opinion that the way he explain things in a layman way, no one does it.
Okay.
I mean, so you can probably talk to him, because you can understand how, if you're struggling with something, to go back and understand this, how to make it easier and make it, because probability statistics and all, when we are also going through, we are finding it very difficult. And then then he joined and he explained the things like a 2-year-old baby can also understand.
Okay.
So we have to get to that level, because we are also always thinking and saying that we are going to provide Stanford level of teaching, right? We are
Hello. Hey, Aditya, I can't hear. Anindya, I can't hear you. I lost you there. Hello. Hello. I'm audible, right, guys? Okay. Hmm. Okay. So I guess Anindya dropped off. I believe we are learning new and difficult things in at these last part of the course in a pretty quick manner. Maybe we should have given more time for these deep learning techniques. Okay. Feedback taken. So Anindya, I totally understand your point of view. I hope he's still there. Anindya, I believe I am audible, right? So I'm just going to uh, put forward my point of views. Okay. See, I'm not taking anything personally. I have been getting feedback that my way of teaching is generally more technical in the sense that I expect a certain understanding of the topic before this thing. Because, see, I'm someone who has done research, right? And I'm biased towards that. And what's nice about Verma sir is he knows the research part. He spent 10 years on top of that to learn how to teach, right? His experience in teaching is way more than mine. Okay, that is number one. Uh, if your issue is with the way I explain things, if your issue is with you not being able to grasp topics or you not being able to make it interesting, what I would suggest is, since you already have access to the Verma sir's lectures, maybe don't listen to me at all, right? I mean, that is, I won't take it personally. See, everyone has different ways of teaching. Everyone has different ways of learning. I am not saying that I'm a better teacher than Verma sir. I personally appreciate his way of teaching. I've learned a lot from him. I'm trying my best to emulate him, right? Uh, so if my teaching is not good for you, it's okay. You can skip these classes. You can take only Verma sir's lectures. Once you have doubts in what Verma sir teaches, I'm always open on Slack, right? I'm always open on Slack, right? So you can come to me on Slack and take it. Anindya, if you raise a, so Anindya, I know personally that at least 5 or 6 students have access to Verma sir's lectures on NLP. My request to you is raise a support ticket and ask them. They will give you Verma sir's lectures. 5 or 6 students in your batch have already taken that route. Okay, so you won't be the first one. Okay, so Anindya, what I can do from my side to help you personally is you can give me the support ticket, you forward me in the thread, I will make sure it's added. I will do that. Okay, I will do that. As for the second part, which is batch homogeneity, right? I have tried my best from the beginning to make sure I go slow. I've tried my best to give intuitive explanations. I've tried my best to focus both on the technical and the this thing side. So I will completely disagree with the feedback that I have not taken steps to make sure everyone is included. Okay. At least the people who want to listen to me, people who believe Verma sir is a better teacher, I cannot help them, right? See, I am limited with my abilities. My strength lies in research. My strength lies in technical things. My strength lies in being able to empathize with students and change the way I teach to do them. If after all the effort I put in, I'm still not good enough for you, it's okay. I'm okay with that. It's perfectly fine. I know I'm not perfect and I don't even want to be, right? I want to learn and I want to build my way to perfection. I know it's a long and tough process. I will do that. So if your issue is with me, my request is don't attend my lectures. You this thing. You please take Verma sir's lectures. You please go ahead with that if that is the best way for you. If you're not able to get access, I will help you get access, and then we can leave it at that. Batch homogeneity. The issue with batch homogeneity is this, right? I already told you that I've done my best to take care of this. If your issue is with the way if your issue is with the fact that I don't have experience in this field, let me tell you one thing. This field is one, okay? Technical details are the same. Deep learning is a field in itself. There is nothing that I lack which I cannot explain. Okay, this I'm very confident on. You can test me today for NLP, any topic. I will be able to get that. Okay. So at a personal level, when it comes to preparedness, I will not listen to you. I know what is required at a PhD level. I know what is required at a research level. And I'm supremely confident I have the abilities to understand as well as teach those things. So teaching style. So one thing which Verma sir does to some extent to make things easier to digest is he relates it to day-to-day things, right? I know that if we just limit our discussion to that, if we don't go in depth, we may miss out a few details. So from my research experience, whatever I have seen, I try to bring to the class and I try to say that, okay, see, this is okay. This is at a conceptual level, but there are some more technical details there, right? So if I point out to those technical details, I don't think I'm doing anything wrong, right? Because see, that is what I'm trying to say. Your starting lines may be different. Okay, your starting lines may be different. Your finish line is the same, no? So I mean, if your finish line is the same, if your final goal is to not only do well within your batch, but also do well on the global scale, okay. So then that I don't know what to do here, right? So yeah. As for the third one, retention being an issue, guys, I believe I'm the only instructor who spends 20 to 30 minutes recapping a topic I've already taught. Okay. I have seen a lot of people teach concepts, and I've seen a lot of instructors at Scalar teach concepts. A lot of people recap, but I spend more time recapping because of this issue, right? Because I'm aware of this. So from my end, I believe I've done my best. Yeah, I'm not interpreting it wrong in India. I'm just trying to see this, okay? There is no personal feeling here. See, at the end of the day, we all want the same thing. We want the students of Scalar to succeed. On the way, if I get a few personal feedbacks, I will not take it personally. I know how to do that. Okay. But I'm also a human being. If you stop in the middle of a class and you tell me, boss, I don't understand what's going wrong here, I will also react emotionally. Right? I mean, it's I'm human. I cannot hold myself back so much. Also, I'm not a robot. So maybe I may have taken or interpreted things in a personal level. I apologize for that. All I'm saying is, let's still keep our eyes on this goal. Okay, let's keep our eyes on the finishing line. I still want to make sure that no matter which batch you come from, no matter what your background is, no matter what your complaint is, I still want to make sure that I'm doing my best to take you here. Okay. So all I'm requesting from you is this. I will do whatever it takes to get you here. If it means I have to get you access to Verma sir's lecture, I will do that. My only thing is, please don't let my way of teaching discourage you, right? What will be the worst thing for me personally is if I have made you feel like you're lesser. That is not my intention. If I have made you feel like, okay, I cannot get this, that is not my intention. If I do that, then I will not forgive myself. See, I will forgive myself for all the other aspects. But if I have done something to discourage you, that is very bad, right? So my only request is this. What can I give me an answer as to what can I do to make sure you're not discouraged? Everything else can be dealt with. See, you don't want me, I'll go away. That's fine. But I at least want to make sure you're not discouraged that you will quit. That is the worst possible outcome for everyone, right? So what I would request from you guys is, what if I'm discouraging you, please give me honest feedback. Is there something I do which is discouraging? Like, I want this from you guys right now. Is there something in the way I teach which discourages you from learning? Okay. Okay, cool. So at least that is not happening. That is perfect. Okay. So that is good for me. Thank you so much for being forward, guys. I really appreciate it. So Anindya, I believe, had a problem with me saying that initially. Okay. So my bad. I totally get this. Okay. So Anindya, like I said, I'm a human being. When you make a question, I will answer this emotionally, right? So you can take that statement which I made initially, that you're not doing your part from your end. Me blaming you that way is not correct, right? Because see, even in ISC, if you go to a professor and ask, I'm not able to do this, he will say, you're not doing enough. This is standard reply. So I was just giving that standard reply. I apologize if it made you feel bad. I totally understand that you're putting your best, right? All I'm saying is, try to use me to do better. And trust me when I say that I'll do whatever it takes to help you do better. The outcome which I don't want is you not reaching this finish line. Okay? That is the outcome we want to avoid. Apart from that, if there is anything I can do to help you reach better, let me know. I will do that. That's all I can say now. As for batch homogeneity, retention, like different scripts, these things. Now this is a little bit late to address this, right? This is a little bit late to address this. A lot of people tried going to the scalar management. What we felt at that time was, looking at your performance across PSP and everything, we thought that no, this is going well. We should continue this. So we were a little taken. We were a little this thing, right? We were a little wrong in the sense that maybe CV I was teaching better, but NLP I'm not. So I will take that into account and I'll see what to do. But all I'm saying is this, okay, guys, let's end this conversation at this note. I'm here to help you reach your goal. That is my job as your instructor. You can insult me 100 times. You can insult me or whatever. You can do all that to me. My role does not change, right? Because it takes a lot more patience to be a good teacher than to be a good student. So all I'm saying is, don't react badly to this. Okay, whatever happened here, it's cool. Okay, see, I will forget. My only thing is, if you I just want you to be brutally honest. Okay, come back with your honest feedback. I will see what to do. That's all. So that's all. I mean, that's where I want to end this conversation. My request to you is, if there is anything I can do, if there is something I can change in the way I do things, I will learn that and I will do it. That's all. So I want you to have a little bit of trust in me that I will have your best interests at heart. I want to get you to this finish line. If you come to me with correct feedback, I will take that into account. I cannot go back in time and change these things, but from this point on, whatever I can do, let us see. Yeah. Hey, it's okay. It's okay. No, Anindya, I'm not feeling bad. See, I'm again telling you, I feel bad for like first 5 seconds, then I forget it because I have been through this many times. See, as you grow older, you get into these uncomfortable situations, right? You get into these uncomfortable situations, but the point of being a grown up is you know how to get out of them because we want to build towards something productive, right? We want to go somewhere where everyone wins, not just where one person wins. So to be positive, you have to not take your emotions seriously. I'm capable of doing that. So you don't have to worry about hurting me. That's what I'm saying, right? All I'm saying is, I know a lot of these issues cannot be solved now. Please come to Slack. Tell me what I can do better. If you're having problems with one concept, if you want me to repeat stuff, I can do that. Come to Slack. I'll take your doubts. And as for getting Verma's lectures because you learn better from them, I'll do whatever it is in my power to get you access to that. So if apart from this you have any feedback, let me know. We'll work on it. That's all. So, and just one thing to everyone else who is in the audience who has been listening to this, right, guys? This is part of learning. These are human conditions. Like humans, despite these problems, have been able to create so much, right? And what we're doing here is we're trying to understand how to get there, right? If even if we get to this finish line, these issues will not go away. Emotions will come into the picture. Things will get heated. It's okay. This is required to do better, right? So my request to everyone also is don't take this in a negative light. Whatever happened, conversation between me and Anindya, I'm sure a lot of you feel similar things. If you have issues, please come forward and address them. At Scalar, we have nothing but your best interests at heart, right? So from that point of view, please reach out whenever you need. Anindya was brave enough to do it, and I respect him for that. Uh, just try and understand that we are not immature people. You say change this, we will do it. We will not shy back. It may seem sometimes like, okay, we're not able to deal with it because we have also constraints, right, on our end. So sometimes we are a little rigid about some things, but overall, we like to listen and improve ourselves. So if you have those kinds of things, please come forward. Don't take this as a negative thing. These kinds of discussions are required, they're important, and they need to happen for us to grow as people. So that's all. For the rest of you, I just wanted to say that there is no hard feelings. I'm very happy that somebody actually came forward and said this. I will take this into account. We'll do the best we can. And yes, let's move on from this. Let's become better. Thank you so much, Anindya. Yeah. Cool. What I'm going to do now is I'm going to end this session here. Kind of not, I don't think it's possible for me to answer any technical doubts at this point. I'm a little saturated. What we can do is if you have any doubts related to transformer architectures or if there is anything I could have explained better, you can reach out to me on Slack or we can do it next class. So maybe the first 10-15 minutes of next class, I will take just your doubts and then we can move forward. I'll also make sure I revise these concepts so that it's not too, it's not too difficult. Like it should not feel like it's bad, right? You should not feel bad like it's not possible. That's all. As long as I'm not doing that, I'm good. So yeah, cool. So yeah, thank you so much, guys. Thank you so much for being honest, for being straightforward. Thank you so much for being patient with me. I know I'm not the most intuitive person, but I'm trying to get better. I'll try my best. And I expect you also to put in as much effort as I am. As long as we're doing this, we'll all grow, and that's where we're good, right? So good night, take care, and I'll see you guys on Wednesday. Thank you. Good night. Yeah.